Okay, fine. Then I'll take care of it.
Yeah.
Okay.
Yes. I mean, you're the boss. So I mean, you decide.
Okay. All right. Thank you.
And so it's 55 minutes plus 5 minutes. Is that right?
Yes.
Yeah.
Right.
So Spencer, you'll tell me maybe 5-10 minutes, something like that.
How do you want me to tell you?
10 minutes before one warning and 5 minutes.
I think so. I thought that way actually.
Yeah. If you, I think maybe, during while the screen is on this thing, I think you can just also interrupt and just say 10 minutes.
Say 10 minutes.
10 minutes and then 5 minutes maybe, and then.
Yeah, I'll just do that. Otherwise, it'll be hard to draw your attention.
Yeah, it's no problem at all.
So you think your talk will be more than an hour, or how do you?
So of course I don't know these things very well, but I've tried to. I think it should be done in 55 minutes. I hope, especially if there are no questions in the middle, it is easier.
Yeah, no questions actually. But you know, I was just thinking from advisor to student, it might just go on and on and on and on. Once it went 2.5 hours.
Hi.
Hello, hi Sunil. How are you?
Hi Spenta. Hi Rajesh. Hi Sudhakar. Thanks, Alok.
Thank you.
It'll just come in a minute.
Sure.
Sunil, I see you're wearing a sweater. Is it cold in Pune or you're unwell?
Yeah, it's winter in Pune. It's not cold, but it's a bit chilly.
So how cold does it get there? I mean, temperature-wise?
At night, it can go down to 15 or 12.
Acha, that must be cold for Pune folks, huh?
Well, it's normal here. And I have a flat which is just cool all the year round naturally for some reason. It's near a lake. So actually, I have very good summers. So
yeah, I mean that's essentially what counts, right? I mean,
it is really. Yeah, we never use AC. We never use fans in Pune. I think only 2 months a year you ever use a fan.
Really?
It's a bit like Bangalore that way.
Wow.
I don't know, Spenta, how is it in Bangalore?
The weather is very pleasant. Actually, it's still raining, you see.
We don't get that kind of rain though, luckily.
Yeah.
We are having nice bright sunshine.
Yeah. So it's a little dark. So it, I wish there was more sunshine actually.
Yeah, my memories of Bangalore are always a bit dark, but that's because I go to this Academy guest house, which is in that dark campus with those very tall trees. You know, you look out of your window and it's just like being inside a deep forest.
Yes,
Bangalore always feels dark.
Yeah, well, yes, there has been a lack of sunshine. But today morning, it's quite bright, actually.
Hi, Ashok.
Hi, how are you?
Hi, Ashok.
Hi.
Hi.
Hi, Ashok.
Hi.
It's really, it would have been much nicer if we could all be in the same place. But at least this is happening after a gap. I mean, this is like what, 2020. So it's a year late, no?
Right.
Yeah, in ICTS, I think the students and postdocs have arranged some gathering, right?
I see that.
Yes.
ICTS AV team is setting up frantically in that room.
Madhava. In Madhava, they have.
Oh, Gyan has come. Hi, Gyan.
Hello. Gyan Maharana. After ages.
You're muted. We cannot hear you.
Hello.
No, you can.
Now we can hear you.
Hi, Jan. Yeah. Seeing you makes me feel almost as if I'm back in Puri.
Yeah, really.
Yeah. You feel like a kid, huh?
Sorry?
You feel like a kid.
Not so much like a kid, just like a hungry person who's expecting you to bring some interesting sweets in the evening.
Hello.
So guys, with your permission, I think we are about to hit 9:30. So should we start? I mean, I see Professor Chaturvedi, our director, is also on board. So I think maybe we can start.
Yes, I think so. Yeah.
Okay. So all right, folks. So a very warm Roorkee style Namaskar ji, and the good morning, good afternoon, and good evening, depending on whatever time zone you're logging in from today. And welcome to the 10th installment of the biennial international conference, strings conference series organized by the Indian strings community, called the Indian Strings Meeting, nationally, ISM 2021, hosted this time by IIT Roorkee. So without further ado, I would request our director, Professor Chaturvedi, to kindly inaugurate the conference and say a few words. Professor Chaturvedi, please.
Thank you, Alok. I'm delighted to be in the company, albeit online, of some very distinguished physicists, more precisely string theorists. It is my pleasure to formally inaugurate the 10th edition of Indian Strings Meeting, a biennial international conference. I understand ISM was born in 2002 at Allahabad, and congratulations to the string theorists of India for not only having sustained ISM over a long period, but also having built upon the foundation laid in 2002 to have useful and impactful meetings every 2 years. On behalf of IIT Roorkee, I'm delighted to welcome the speakers and participants of ISM 2021. For the first time, I understand ISM is being organized entirely by an IIT, and I'm happy that it happens to be IIT Roorkee. The fact that it is happening in the 175th year of IIT Roorkee makes it all the more special. As some of you may know, as we approach our 175th year, we are scaling new heights in terms of attracting the brightest students and faculty. For the first time, a student in the top 100 of JEE Advanced has joined IIT Roorkee. This student is ranked 32. Let me briefly also talk about our physics department. It's a fairly large and busy department. Apart from the PhD program, the department offers a 2-year MSc program through JAM, a 5-year BSMS program through JEE Advanced, a 4-year BTech in Engineering Physics program through JEE Advanced, and 2 MTech programs through GATE. I wish it was possible to organize ISM 2021 in a physical mode. That would have given the delegates an opportunity to experience our wonderful campus. I hope meaningful academic interactions will be possible despite the online mode. I wish all the speakers and participants gain by being a part of ISM 2021. Thank you for giving me this opportunity. Thank you.
Thank you, Professor Chaturvedi. Thank you so much. Okay. Maybe okay. All right. So
Alok, there's music coming.
Alok, you are muted. Alok, you are muted.
Sorry.
Alok, there's
sorry,
music coming from someone. You have to mute that person.
Yes.
I hope you have a team to mute random people.
Oh, yeah. So talking about the team, that's a great point. So with the kind permission of our chair of the first session, Professor 𝗦𝗵𝗶𝗿𝗀, the founding director of the International Center for Theoretical Sciences, Bengaluru. And I guess one of the folks who basically, I would say, acted as a seed for the string theory group at TIFR back in the day. So I want to actually have the backbone of ISM 21, which is the tech support team, consisting of a trio of integrated MSc third-year students. Just with your permission, turn on their cameras and just wave to us, because in my humble opinion, it's always good to assign faces to names. And the names are beautiful. I mean, it's the names say it all. We've got Mohak, we've got Shubham, we've got Lucky. What do you want? So guys, can you turn on your cameras and just wave to us? I have no idea whether they're visible. Maybe one has to scroll.
No, they are visible actually. Hello.
Okay. So thank you, really guys. Thank you so much. Thank you. And so I think, and one last thing with Spenter's permission, this is exclusively targeting with these very selfish motive of motivating those bright undergraduates who are, I think, logged in today, are going to be logged in for the remainder of the conference, especially from tech institutes. So the speaker number one, day one, session one, is 1987 All India Rank 1, Rajesh Gopakumar, the current director of ICTS. I pray that serves as a huge motivation for quite a few of our students to actually pursue theoretical physics as the first option. So I should shut up now. I apologize. So I request very humbly Spekta to please take over. Spekta.
Okay. So thank you, Alok, for your kind words, and welcome everybody. Good morning, good afternoon, good evening, wherever you are all on this little rock in our solar system. And the first talk is going to be by Rajesh Gopakumar, and I'm looking forward to a very electrifying discussion about this important seminal work on the string phase duality. The title is From Fields to Strings and Back. Rajesh, take it away.
Thank you, Spekta. Thank you especially to Alok and his team for putting this together and getting us all, at least virtually, together at this difficult time. It was actually very nice to be reminded that this is the 10th anniversary of the ISM, because 2002 we had it at HRI, and it was a really wonderful beginning to this whole thing. Of course, there were precursors at Puri and so on, and Gyan had organized a number of events to bring people together, but I think the string community as a whole probably came together at HRI, and it was it's very nice to reflect back on that time. Many of you were there, and I hope next time we will be able to meet in person, but nevertheless I think Alok has made it as nice as possible by bringing us together. So okay, so let me share my screen. Okay, it's visible, I hope.
Yes, it's visible. That's fine.
Yeah.
Please.
So, thank you for inviting me to give this talk as well. And I will give a sort of an overview, a little bit more pictorial rather than in terms of there'll be some details, but I wanted to try to give you a certain picture of an approach to try to understand gauge string duality in sort of a first principles way. And a lot of the work, at least the more recent work I will be talking about, is in collaboration with 𝗦𝗫𝗶𝗿, and very recent work in the last year or so with a number of people. And I want to highlight 𝗦𝗫𝗶𝗿, my student who is here, Matthias's student Bob Knighton and Andrea Day, and two VSRP students from the ISER system, Bhopal and Mohali, Faizan and Bharat Kumar. So yeah, so this is a sort of a broad outline of the talk. First, I will try to sort of motivate what I'm trying to do about this approach to derive ADS-CFT, and why free fields are the best place to start in some sense. And some of you have heard me give this motivation, but for the younger people, I think it might be useful. And then I will outline sort of a passage from fields to strings in a very general context. And this is something, it's sort of almost 20 years ago that this sort of outline kind of started taking shape. But more recently, in the case of the ADS-3 CFT duality, in a sense, this passage from fields to strings has been very explicitly realized. And so you can actually see the nuts and bolts of this thing happening in a very concrete example. And then I will try to go the other way around and see how this ties up, and in the ADS3 example will be our jumping off point to go from strings to fields in this, and this will involve proposals for the tensionless limit of the world sheet theory in the ADS3 CFT2 case, which will, and a generalization of that, a proposal for the free Yang-Mills theory, the super Yang-Mills theory, and in some sense I'll try to close the circle from fields to strings and back. So okay, so that's the plan. So the overarching question is, how exactly do large N quantum field theories reorganize themselves into theories of strings, something that had been intuited by 't Hooft nearly maybe half a century ago almost, and which of course received a lot of impetus from the discovery by 𝗦𝗫𝗀 now about a quarter of a century ago on how deep brain physics tells you a sort of a gives you a way in which you can see this or gives you a number of examples where this happens, and the underlying mechanism seems to be a kind of an open-closed string duality. And this picture that I like to flash is kind of a cartoon of that, about how when you sum over the holes of an open string theory describing D-branes, there's a back reaction which alters the background, at least at large 't Hooft coupling, and in some sense you think of it as a closed string background in the dual space-time. And this is, of course, how 𝗦𝗫𝗀 originally arrived at it, by looking at the near horizon geometry of D3 branes and so on. But to actively implement this idea is very difficult at large 't Hooft coupling, because firstly, there are an infinite number of holes. You have to sum the perturbation. This expansion is a sort of you'll have to sort of resum the whole expression, which will lead actually to a change in the background, the back reaction that I mentioned. This is so it's been a very interesting idea, but but it's very difficult to actually see how it works. And this is why all of our understanding of gauge string duality is through numerous examples from various deep brain configurations. So typically deep brain configurations where we have a sort of a bulk or a gravitational description of the deep branes as well as some geometries. And so if I think of the phase space, so to say, or the very minimal phase space of parameters involved, there's one which is the vertical direction, which is the quantum nature, the quantumness of the theory. And that's measured in the gauge theory by the 1/n effects or string coupling in the world sheet description. And then there's the horizontal axis, which measures the stringiness of the description, and there's one side which corresponds to the large ADS radius, which is described very well by classical gravity and its higher derivative corrections. And this parameter translates into the 't Hooft coupling of the field theory. This was the large 't Hooft coupling or the strong coupling limit of the field theory. But there's this other corner, which is the perturbative quantum field theory limit, in which the 't Hooft parameter is very small, but of course the ADS is then very highly curved or tensionless. It's the extreme stringy regime. And this is the sort of typical dictionary you have. So, but the advantage of looking at this side is that we know what perturbative quantum field theory is. And in particular, in this open closed string duality, there's only a finite number of holes to sum over, definitely at zero coupling, and then you can sort of stratify it by the usual Feynman diagram expansion as you go away from there. There's of course a well-defined genus expansion still at zero coupling, and you can, if you go away from zero coupling, you have the whole machinery of perturbative quantum field theory behind you to understand them. And indeed, what that machinery is basically computing free field correlators or Wick contractions. And we'll focus on two test cases to sort of, when we'll shift focus to this end, as I said, this is the motivation part I mentioned, we'll shift focus to this end, and we'll focus in the rest of the talk on two particular examples where we'll look at the tensionless limit of this dual string theory, or from the gauge theory point of view, focus on free theories, namely the so-called free symmetric orbifold over here, or the free n=4 super Yang-Mills theory over here.
Rajesh, can I ask a question about that diagram?
Sure.
About that picture?
Yes.
Somehow you seem to be implying that we can, the lampposts are really bottom left and bottom right. But
yes.
Isn't it possible to go up by considering a solvable field theory, for example?
Yes. Yeah. So free field theory, of course, you can go up here.
Not just free, I would say. I mean, you could take a 2D.
I mean, you can in the perturbative regime. Yeah. So this, and perhaps there would be integrable models in which, and in some sense, in n=4 Yang-Mills and many other theories, you can go quite a bit here. You have many exact results in the 't Hooft coupling, so you can go both horizontally and to some extent vertically. Yeah. So, but this is the canonical case. I just wanted to focus on those two because those are the places I will be mostly working on. I will be working at very large n, so I will be mostly looking at things in the genus 0 on the worldsheet, and yeah, so that's the regime, but we can talk about other extensions as well.
Thanks.
So I want to say a couple of words about what would constitute, at least in my eyes, a derivation, at least the beginning of a derivation. And I'll take as an operational definition the equality of Euclidean correlators on both sides of the duality. Now, there are many, you can consider Lorentzian correlators, you can consider non-local operators, there's many other things, entanglement, entropy, various measures that are there, but I will focus on this limited class because I think that already gives you a lot tells you a lot about the innards of this duality, and then one can hope to address others. So for this class of observables, the idea is that you're relating single trace operators on the left-hand side. So these O's are things in a gauge theory which would have a single trace of a gauge invariant. So it's a gauge invariant quantity, but with a single trace. And they are labeled by positions x1 to xn. So the x's for me will always denote the position of the field theory variable, and we are looking at a Euclidean free theory, which is conformal. So we can think of it on the sphere, the d-dimensional sphere. And these are other labels, which H's will be essentially the conformal dimensions, and W's are other labels which you needn't bother about right now. Now, the fact that the field theory has a well-defined 1/n expansion means that you can pick out the genus G contribution of this correlator, and the idea is that it should map to the genus G contribution of the corresponding string amplitude, which is also given by a worldsheet correlator. Now it's on the two-dimensional worldsheet of the string. So this correlator, the Z's, will define the worldsheet coordinates, and we'll compare genus by genus. So here it will be a correlator on a Riemann surface or a worldsheet of genus G with n punctures. N is the number here. And then, of course, we are instructed to integrate over the moduli space of all these world sheets. And that's what this right-hand side represents. And these are the physical vertex operators of the closed string dual. So it's a statement of this equality for all n, all g, all x's, all w's, etc. So it's a very vast kind of equality that you want to match. So this is.
I have a question.
Actually, I think if we can have the questions at the end, I think that would be better. I think that was. This, of course, when I write such an equality, it presupposes a dictionary between the single trace operators and the vertex operators. So that is essentially a statement about the matching of the spectrum, that the single trace operators correspond to physical single particle states of the string theory, and there's a match of the conformal dimension with the sort of the space-time energy of the dual string theory. Now, the nice thing which I like about this operational definition is that both sides over here can be in principle autonomously defined. The left-hand side is a quantum field theory correlator at a fixed point. I mean, it's a free theory, so it's sort of trivial in some ways. And the right-hand side also, we believe, at least it's not guaranteed, but the working hypothesis is that there is a sigma model, a two-dimensional CFT on the right-hand side, and these are physical correlators. That sigma model can be quantized in the usual method, and this right-hand side it gives you a physical correlator of that dual string theory, and there's an integral over this moduli space. And so, in principle, it's a mathematically well-posed question. And one of the main goals is to try to make this equality manifest. I mean, of course, you can check case by case, and that'll be, you get confidence in a duality, but to ultimately understand it, you want to, in a way, tautologize the correspondence, or say that this side is manifestly the same as that side, because it's, I think, our job as physicists to sort of demystify this remarkable equality. But I want to point out an apparent asymmetry in this equality when we kind of try to match these sides. At first sight, it seems almost as if if we are trying to, if it's easier in some ways to go from strings to fields, because if you can try to compute this correlator of the 2D CFT and then integrate it, and you can try to do this. But going from the other way, from the left-hand side to the right-hand side, in some ways, you think you need to reconstruct this world sheet integrand, and that is, of course, not unique. You can have total derivative terms, or in the language of the usual string theory, BRST exact terms, etc. Nevertheless, I think that, as I will try to argue, there is a canonical or a natural way in which you can go from the left-hand side to the right-hand side. And that was the ideas I was developing almost 20 years ago. And the basic idea, and I'll flesh it out a little more in the next few slides, is that, and this is now I'll going to the second part, the sort of the general passage that I'm going to, this thing is actually in the left-hand side also, there is a hidden sum. This side, you think of the integral on moduli space as a sum over the world sheets of the string. But the left-hand side also, when we actually evaluated, you sum over different Feynman diagrams, which are in a sense distinct world line topologies of the corresponding gauge theory or the field theory. And so there is a sum on this side, there's a sum on that side. Now that seems to muddy things even more. I mean, now how do you kind of try to make a correspondence? So the claim is that each Feynman graph corresponds to a closed string world sheet. So that sum is, in some sense, you are trying to equate the summands or the integrands on both sides. So the strong claim is that each Feynman diagram corresponds to a closed string world sheet, and there's a very canonical way to do this. And this was the proposal which exploited a certain parametrization of the moduli space, which is very tailor-made for this open-closed string duality, and in a way, I think really implements it mathematically. And this I will explain a bit this Strabel parametrization of the moduli space. But I just want to point out at this stage that this is in some sense refining the 't Hooft's original idea, where 't Hooft assigned a genus to each Feynman graph. So it made a correspondence between a class of Feynman diagrams and a set class of world sheets. Now you're going further and sort of assigning each Feynman diagram to a particular world sheet. And there's a and this basically the geometry underlying this treble parametrization is that of gluing strips. So you can, 't famously taught us that you can think of the Feynman diagrams of the large N theory as sort of these double line strips, which we now think of in the D-brain language as open string world sheets. So these strips can be glued in a very canonical way to form the closed string world sheets, and this is what we will try to exploit. So,
can I interrupt? There is
yes,
an
please.
overwhelming request to take short questions from a lot of people. So I think we can just do that. But I'll in case it goes too long.
So I'll leave it to your judgment.
Sure. Okay. So anybody has a short question at this juncture can ask, please.
Yeah. So I have a question. By free, do you mean that there are no interaction vertices?
So the free theory will be defined as the limit as the G-Yang-Mills coupling goes to 0 of the n equal to 4 Yang-Mills. It will be given by, so when we are considering these correlators, there will be no internal vertices. Of course, there will be external vertices, and there will be big contractions between single trace operators.
But how can there be external vertices if there are no internal vertices?
I mean, there are gauge invariant operators in the Yang-Mills theory, which are products of whatever the fields are. So traces of single trace operators, and the whole definition, the physical observables in the free Yang-Mills theory are these correlators. So you can represent them diagrammatically. It is something like what I have here, that you have these, in fact, these Zs over here are vertices. So you can think of, I mean, here I've drawn many Feynman diagrams, but if you count the number of contractions, that's an operator trace with phi to that many this thing. So that's the left-hand side of the equality that I was mentioning. So you can consider product as this is, in this case, there's a 4-point function. There's point at infinity as well, which is where all these lines go and contract. And so it's a 4-point function of traces of single trace operators with a finite number of fields in them. And so you're considering all these big contractions. So if there are no further questions, let me explain this a little more. So this canonical picture that I was mentioning is the following, and so this is a representation of the Feynman diagram. Now you can think of this Feynman diagram. So there are all these strips over here. So you can associate a big strip whose width is proportional to the number of the strips of each color. So they are color coded because of the big contraction. So Z1, these ones are contracting with Z4, these are contracting with Z3, and this with the Z2, and so on. So that's why they're color coded. But you can think of each of these individual strips as, firstly, you glue together things which are homotopic to each other into one fat strip of width. You assign a width which is proportional to the number of big contractions. And you can think of these strips as conformal to these quadrilateral regions. And you can associate a closed string surface where the original points are poles, and these strips are all glued together along this thick line over here. So this is what in the previous this thing, oops, how do I go back? So here you could see that there's a kind of a place where all the three things meet, and you get a kind of a graph here. And so this is the That's what, in general, these colored lines here represent. You have these strips which are all glued at these along these graphs and along the edges of these graphs. And the width of each of these lines of the graph is, as I said, proportional to the number of these big contractions. This associates a very canonical, this is a mathematical construction of the moduli space of the closed string world sheets. And just specifying these widths, it gives you a unique point on the moduli space. And so this is a very natural mathematical construction, and it associates to this set of big contractions, a given so-called Streble surface, and these points become the poles of a corresponding quadratic differential, the Streble differential, the original insertion z's, and the vertices of the graph where these where these strips are glued, these vertices become the zeros of the Streble differential. So what is this Streble differential? The Streble differential is a quadratic differential which, as I said, foliates the Riemann surface into what are called horizontal trajectories. There's a technical definition, but never mind. There's a very nice foliation, which is like these closed circles, like isobars or whatever, except at this graph, which is where it becomes a kind of a graph and it has these vertices, which is called the critical horizontal trajectory or the critical graph. So each of these are sort of disks with a single pole of the Streble differential. And in fact, it's with one pole, which is a double pole of the Streble differential. And these zeros are zeros are where this graph has these vertices, as I said. And you can consider the so-called Streble length, which is the integral between two zeros of the Streble differential. And this is what, as I said, it's the width that I was mentioning of the strip earlier. And these lengths are what parameterize the moduli space. And we'll often consider the case where these lengths are integers, and because in the canonical way to associate to a free field big contraction, like in my previous figure, was to the number of big contractions. And so we'll often consider that case, and I can discuss more later. So that's the sort of the general picture. Now, I must stress, this was a proposal. This was a proposal when I was making it many years ago, and you can believe it. It of course had a certain level of plausibility and this thing, but it's a proposal for how to associate world sheets to world lines. The very nice thing that happened recently was in the context of the ADS3 CFT2 correspondence, you could actually see this explicitly realized, and without having to sort of make any proposal or guesses or anything like that. It just came out of the box, so to say. So firstly, what is so for ADS3 CFT2, a couple of years ago with Lawrence Eberhardt and Matthias Gaberdiel, we made a proposal for the dual, for the tensionless limit of the ADS3 CFT correspondence. We identified the tensionless limit as the point of this, let's say, with the T4 compactification, this background, with 1 unit of NS flux through the ADS3 and the S3. And we claim that this is the same as the symmetric product of the T4 theory, in this case in the large N limit with these couplings. So the symmetric product is CFT is a very well-studied two-dimensional CFT. It has arisen in the context of the black hole microstate counting and so on and so forth. And this left-hand side is you compute correlators of so-called single cycle states, analog of single trace operators. And now it's on a two-dimensional sphere because we are in 2 dimensions. The boundary theory is on the S2. And this side is a string theory, which is also well-defined because it's a theory with NS flux. And you know a world sheet description of this side as well. But let me, since we are still on the fields to strings, let me concentrate on the left-hand side. And the left-hand side, the correlators are computed. It's been known actually since Lunin and Mathur, again about 20 years ago, that there's a very nice way to compute correlators in the symmetric orbifold CFT, which is similar to how people compute things in CFTs with using the replica trick. So what you do is you can, instead of computing the correlators directly off this T4 CFT, you lift the correlator to an auxiliary space, an auxiliary two-dimensional surface on which the fields are single valued, and you have a T4 CFT, not this symmetric product. You just have a T4 CFT, but you have a more complicated worldsheet, which is a covering space of the original space-time, the S2. And in fact, it was even guessed at that time that this covering space seems to play the role of a worldsheet. And now actually we see this very clearly realized. But in any case, I will come to the string theory a little later. So the idea of the Lunin-Mathur computation is that you can compute this side by summing over contributions from various covering maps from this auxiliary space, or aka worldsheet, to the S2 over here. And for fixed number, if I fix these xi's, as I would normally do, there's a discrete number of these covering maps. If I fix all these branching data, which is the xi and the degree of this branching, which is, by the way, related to the twist of the cycle in the orbifold theory, the length of the twist of the cycle, and in this side will be related to what is called spectral flow parameter. But in any case, this is the part of the branching data that you specify when you compute these correlators in terms of these covering maps. And there are actually a discrete number of covering maps, and there's a nice way to associate them with Feynman diagrams. Each of the contributions to the correlator here can be associated to a Feynman diagram, much like a free field Feynman diagram. And this was pointed out by Bachman, Rastelli, and Razamat more than 10 years ago. And just to give you a brief idea of what it is. So if we are computing a 4-point function of, and this X is my space-time, the two-dimensional sphere where the CFT lives. If I'm computing a 4-point function, I draw a curve through that 4-point function, and which encloses, let's say, x equal to infinity. And I draw a solid curve, and I kind of have a dashed curve through it, a bifundamental line that I draw. Now I pull it back by this covering map. There is a covering map from this auxiliary worldsheet space, the Z space. And it's a multi-cover, so there will be multiple images of the pre-images of this. This shaded region will go into, in this case, 3 shaded regions. Each of these will be poles, the pre-images of the poles, or the poles of the covering map, gamma of Z. And so there's a Feynman diagram. This side begins to look like a Feynman diagram. And in fact, when you have a very large covering map, you can begin to see it starts becoming really like a usual big contraction Feynman diagram. And this is sort of the neighborhood of between 2 vertices I and J. You have multiple of these pre-images, etc. So you can have multiple big contractions between vertices, and there will be a sequence of these poles, these pre-images of these poles of this covering map. And the thing that was very nice is that in a limit, when you take this twist or the W's, the cover, the branching data, the number of big contractions to be very large, these poles start coalescing into cuts, and you start getting these cuts on the dual on this covering space. And in fact, this becomes precisely the Streble graph. You can actually show that. And it's very nice because there's a very canonical thing you can associate, a canonical quadratic differential you can associate to the covering map, which is the Schwartzian of the covering map. And the Schwartzian of the covering map in this large twist limit actually becomes this quadratic differential that I mentioned, the Streble differential. It has exactly the properties that the Streble differential I mentioned has, namely it has these double poles and this real lengths and everything. So it is the Streble differential, which is normally very hard to find explicitly, but in this large twist limit, it takes a very simple form, being the Schwarzian of this covering map. So this is what I was saying, that now for at least for large twists, you can see that each Feynman diagram, and namely each of those pictures that I had in the previous slide, corresponds actually to a point on the moduli space where the Streble lengths are proportional to the, in fact, the Streble lengths you can now see from the definition of the Schwarzian. Again, you don't have to propose anything. You see directly from the Schwarzian, the definition, from the fact that the Schwarzian is the Streble differential, you see that the Streble lengths, this integral bit along these, the integral along these between these zeros, these are proportional to the number of the Wick contractions. In a way, it just comes out. This comes out through a very nice auxiliary matrix model whose spectral curve gives the Streble differential, and which is the thing that is the Schwarzian, etc. But I don't want to go into that in detail right now. But the point now is that, in fact, more than what could be said 20 years ago, you actually now learn what the integrand on the moduli space is also. So when I mentioned earlier about associating fields and strings, I talked about associating each Feynman diagram to a string worldsheet, but now the summand itself, each integrand or piece in this sum, you can see what it is, because Luhn Mathur gave you a prescription of what it should be. It is given by a certain Liouville action, and when you compute what that Liouville action is now using this realization, you find that it is this nothing but the Streble area, the area of the graph under the area measured in the sort of natural Streble metric that you associate to the Streble differential. So this is how so you see now the passage from fields to strings very explicitly in this example. And to really close this, you need to show that the string worldsheet also gives you exactly this, and this we were able to show from the explicit form of the k=1 string theory, showed actually that you do get a localization on the moduli space. There are very specific points that it gets contributions from, which correspond to the covering maps. There's normally in the string correlator, you get a contribution everywhere on the moduli space. But Luhn Mathur told you there are only a discrete number of contributions from these covering maps. And the string worldsheet is clever enough to see that there is this discrete set of covering maps. And the integrand is given by, in this case, the semi-classical worldsheet action, which agrees with the Streble area. So you can really close this. And this very unusual localization property on the moduli space, we could understand later that it follows from something like a twistor incidence relation, which will actually play a role in the second half of my talk. Well, yeah, the second half of my talk, which I'm coming to now. So now let me go from the strings to the fields. So that let's see how things start tying up from the string theory side. So for ADS3, as I said, there's a very explicit worldsheet description. You have a free field description actually at this k=1 point, because there's a Wess-Zumino-Witten model based on the supergroup, and it's a kind of a gauge linear sigma model. And despite it being a highly curved ADS3, the worldsheet description is in terms of free fields. It's a bit like the SU2 level 1 theory. This is just a souped up version of the SU2 level 1. Instead of just having some fermions, you now have some funny bosons as well, bosons with the wrong statistics. That's what symplectic bosons are. So, but there's a geometric picture of what this free field description is. There are actually some kind of twistor variables, and this will be important as we go to the ADS5 case. I mentioned this before, that the twisted sectors of the orbifold CFT, which are labeled by the lengths of the twist, correspond to what are called the spectrally flowed sectors, which I don't have time now to explain, but Maybe those of you familiar with this will understand. And indeed, as I said, the worldsheet correlators are delta function localized, and the semi-classical worldsheet is actually at the boundary of ADS3. You can write down the semi-classical string configurations which contribute to the worldsheet path integral, and they give exactly the Lunin-Mathur correlators, as I said, closing the circle in this particular case, I think very satisfyingly. This is sort of the logic of the flowchart. If you're kind of confused, this side is the sort of the field theory side. As I said, there's the correspondence is that there's a Feynman graph, and the dual to the Feynman graph is the so-called Streble graph, which is associated with the Streble differential. In this particular case of ADS3, this Feynman graph was related to these covering map contributions, and through this auxiliary matrix model, you got the spectral curve which has the cuts, and then this spectral curve was in the large twist limit was described by the Schwartzian, which, as I said, turns out to be the Streble differential. And this identification is sort of what is important for connecting with the worldsheet analysis, which, as I mentioned, the worldsheet gets contributions localized at this point, and these correspond to these very special points on the moduli space where the Streble lengths are integers. Okay, so in the remaining 15 minutes, I guess, of my talk, I'll try to say a bit about how this generalizes to the ADS5 case, or what we are proposing for the ADS5 case for free n equals to 4 super-Yang. So this ADS3, as I mentioned, there's a sort of a sigma model description in terms of these free bosons and free fermions, which can be assembled into some kind of ambi-twister variables in the twister language. This viewpoint is perhaps not so significant for ADS3 times S3, where you could think of it in more conventional ways, but I think it is very crucial when you generalize to the ADS5 times S5, where you have the corresponding ambi-twister variables, which are well-known twister description of the boundary theory, and has cropped up in the description of free or tree level n equals to 4 super-Yang-Mills amplitudes in an ambi-twister open string theory. In a sense, what we are proposing is a kind of a closed string cousin of this description based on these fields, which are the natural generalization of the field. So instead of this sigma model, we consider a sigma model now, which in a way realizes the PSU 2,2/4 supergroup relevant for ADS5 times S5. Supporting evidence for this proposal is also the fact that it ties in very naturally in giving a kind of a covariant description to the BMN light cone gauge string theory that people had studied starting 20 years ago, and which led to all the integrability developments, etc. So let me just quickly give a picture of what this worldsheet description is. As I said, there are these twisters fields, and they give a free field representation of the supergroup at level 1. You just construct currents by bilinears of these fields, and you have to impose a certain constraint, which is a very important gauge constraint. So in a way, it's a gauge linear sigma model. You have these free theories with a U1 gauge field, which imposes this Gauss law constraint on the worldsheet. There's this crucial ingredient of spectral flow, which I can't do really justice to, but it's many of you may have seen this in the context of ADS3. It's an automorphism of the supergroup. Basically, you generate new representations labeled by a positive integer W, which you can think of as built from so-called a spectrally flowed vacuum state by the action of these spectrally flowed fields. So you can think of this as a kind of a rotated version of your original highest weight representations of of this this �-𝗏𝗃 representations, but these are non-highest weight once you do this rotation, because now there are some seemingly positive modes which will be, some positive modes which will not annihilate the vacuum, etc. But nevertheless, in ADS3, you saw that they give you very well-defined physical string states. So in any case, you consider this Fock space for each W, and we consider this generated by a finite number of these so-called wedge modes. There's a very canonical set of modes which whose mode number lies in this finite region between W-1/2 and plus W-1/2. So we consider a Fock space built out of the modes which do not annihilate this vacuum, which are about half the modes in the wedge. And then, of course, there are negative out of the wedge modes, which have mode numbers less than this in this interval. So just to kind of give you some anchor, W equals to 0 is, of course, the spectrally non-flowed sector. That's the usual NS sector. There's the W equals to 1, which is now integer moded. And in fact, the wedge you see is just 0, and it has only 0 modes in the wedge. And that's the Ramond sector. And together, in fact, the W equals to 1 sector actually generates the so-called singleton representation of this supergroup. By the way, for those who are familiar with the BMN string, this W will play the role of the P plus of the light cone gauge of the BMN string. That's, I think, a very useful intuition to have. So we make a claim which ultimately should be borne out by a quantization of the world sheet theory, that you can go to a physical gauge of this world sheet theory. So by the way, the original theory has ghosts as well. It has vanishing central charge, then you impose, then you add the ghost system, and we would like to claim that there's an underlying world sheet n equals to 4 structure, which has the corresponding n equals to 4 ghosts, which also have central charge 0, and so that you can get critical string theory. And the claim is that in a physical gauge, all the underlying constraints from the n equals to 4 symmetry, or the large world sheet symmetry you have, allows you to gauge away most of the modes, namely all those out of the wedge modes, and leaving only these modes in this wedge, which correspond to effectively the W bits. And then you consider the Fock space generated by them and impose certain residual physical conditions, somewhat like you impose in light cone gauge, that L0 is sort of 0 mod W. And this, of course, there's the important gauge constraint, that the residual gauge constraint that you still need to impose. And this condition A is, if you wish, some kind of a discrete translational invariance on the world sheet with these W bits. It's a sort of a cyclicity, and this gauge constraint is the very natural one, which is that each of these bits together form a singleton. And this is particularly more natural if you look at the site variables, which is a discrete Fourier transform of these original twistor variables. So phi's are any twistor variables. So this reproduces once you impose this condition, this on the nose reproduces the large N gauge invariant spectrum of single trace operators built with so-called W letters of the n equal to 4 super-Yang-nulls. More specifically, what you get are, you take when the W spectrally flowed sector, you take the singleton representation, tensor it W times, and impose a cyclicity condition, which is what that L0 is equal to 0 mod W imposes. And then you sum over all W from 0 to infinity. W equals to 0 is very trivial. It is just, as I said, the Neveu-Schwarz vacuum. And that's once you impose the physical state conditions, that's the only state that survives. And that's naturally identified with the identity operator in the super-Yang-Mills theory. This W equals to 1 corresponds to single letters. As I said, these are the singleton representations where you just have have single fields. In a SUN Yang-Mills theory, if you take the trace of these fields, you don't get anything, but in a UN Yang-Mills theory, you have this. So in a sense, what you get is sort of more naturally the dual of the UN Yang-Mills theory. Of course, the singleton can be decoupled. And for W equals to 2, just to illustrate what you get from you find that there are physical states with L0 equals to 0, not just mod W, identically 0. These correspond to the BPS stress tensor multiplet, which has delta equals to 2, that is this multiplet with this lowest state and descendants. And in fact, it's a general statement that the L0 equals to 0 state corresponds to all the BPS multiplet. The L0 not equals to 0 mod W, in this case 0 mod 2, the first state is this -2, and that corresponds to the non-BPS Konishi multiplet, this and its descendants. And for in general, -2p corresponds to all the higher spin multiplets. So these are the things with 2 letters, which form the usual higher spin currents from bilinears of the fields. And you can do this for any W, and you see a very nice organization of the spectrum of the free super Yang-Mills, which is in a way a covariant organization, because you're not just organizing now by W, but you can actually further stratify by the eigenvalues of L0. And you see a very nice parallel to the BMN spectrum, because it is now, the BMN spectrum is, of course, in terms of the light cone momentum, but it's very similar to what you have over here, at least at large W, they seem to be the same. Finally, in the last 5 minutes, let me just tell you about something which pushes things beyond the spectrum, and based on recent work with 𝗏𝗏, Faizan, and Bharat. So you can try to build a geometric picture for describing correlators in this case. As I said, after you match the spectrum, the idea is to see if you can tautologize the equality of correlators between the left-hand side, the field theory side, and the string theory side. And in ADS3, as I mentioned, there's a very beautiful picture which allows you to sort of the Lohnen-Mathur picture, which is realizes this equivalence between the realizes this way of going from fields to strings through the Strebel parametrization of moduli space. Can we see an indication of this in the ADS5 case? And this is what we have begun to do here. And you can actually consider now the generalization. There's no natural generalization of the Lohnen-Mathur picture directly, but because that was in a way special to the ADS3. But there's the natural way to generalize is through considering covering maps of the twister space. And once again, look at world sheets which are close to the boundary of ADS5. And what we propose is that these being twister variables, and these are actually the twister variables for ADS5. There's the twister description of ADS5 has a very natural set of, is realized with a natural set of so-called incidence relations, which anyone who has studied twisters will know is one of the most fundamental relations. It is the twister correspondence between space-time and the twister variables. So this twister incidence relations for ADS5, we propose that these hold at the stringy level now as fields. So that's why these are functions of Z, and these are holomorphic functions of Z. And the twister variables, these X's are the boundary space-time of the ADS5, and R is the radial direction. And there's a similar similar set of incidence relations for the others. And now there's a very natural set of reality conditions you have to also impose on the twister variables. And these are Euclidean reality conditions which relate lambda with the complex conjugate of lambda, and in a way with the anti-holomorphic fields. And in terms of them, the twister correspondence in Euclidean signature allows you to solve for the space-time variables in terms of the twister variables. And you see now it's not holomorphic, and that's in ADS5, there isn't a very direct holomorphy in terms of the space-time variables. It's the twister variables which are really holomorphic. And at least in a special set of kinematic configurations when the points lie on a plane or on a sphere inside the boundary, you actually can explicitly write down these holomorphic covering maps, like in the ADS3, for instance, for a 2-point function of trace phi to the W, phi bar to the W, BPS states. You can write down it's a kind of a simple branch cover. The V's are essentially the space-time positions, the different between xi and xj. If you have this corresponds to a covering map for a 2-point function to xi and xj. And you have this explicit covering map and the twisters, and the quite very nice thing that you see is that very parallel to the ADS3 case, you can actually map these variables, these Z variables, to the strip, conformally map them to the strip. And the Schwartzian is actually a constant, which is what you actually have for this treble differential on a strip. And very nicely, this treble differential once again reproduces the propagators of Yang-Mills fields through the so-called treble area, which, remember, in the ADS3 case, I mentioned that the integrand on the moduli space gives you the Luhnen-Mathur integrands. And here you want the Feynman diagrams should give you the Feynman diagrams corresponding to any correlator should give you the Feynman propagators as the weight, and then you sum over all the Feynman diagrams, and you get a very similar picture. I don't have, let me just show you this diagram, that you can have the strip, as I said, and the strip is of width W, and of course, in a multi-point correlator, you can conformally map all these strips. This is the, like in the picture I showed you, to these quadrilaterals. There are many of them meeting at a point, and you can compute the treble area of the whole world sheet by adding up the contributions for each of these quadrilaterals, adding up these treble areas. And the additive treble areas lead to multiplicative Feynman propagators, like you are used to doing in a field theory. You have the product of propagators from here to here. And in fact, it comes out very neatly, because you see that the treble area, in fact, with you need to regulate the treble area because it's that of a strip. And so it's sort of infinite. But if you regulate it with the very natural imposing a space-time cutoff, you see that the treble area gives you the Feynman propagator up to a multiplicative renormalization, which you would normally have to do for each of the operators due to the short distance singularities in the field
Rajesh,
yes.
How long will you take?
I'm essentially done.
Right. Okay.
So this is my last slide. So okay. So that's this thing that so let me just summarize by saying that we've exhibited these test cases, the tensionless ADS3 CFT2 to a large extent, and begun on the ADS5 CFT4 case, where this general program of reassembling large N quantum field theories into string theories can be very explicitly carried out. And because there is a dual tractable worldsheet theory, you can try to close the circle from the strings to the fields as well. And this then holds out the hope that once you understand these cases very well, you can generalize to general large N quantum field theories, because you need not necessarily have beforehand the worldsheet description. The field theory would give you, through this treble construction, description of the dual worldsheet, at least the dual worldsheet correlators. Now, before we do that, there are many other things in these examples itself that needs to be understood better, I feel. One of the most important things is a first principles quantization of the worldsheet theory and getting the physical states from these twistor worldsheet theories. They're very unusual, and they have many complicating features, which is what has made the task difficult, but it's a technical hurdle, which I think will be overcome. There's an underlying topological string nature to all this, and especially if you the localization on moduli space is often is a signature of the topological string description. So many indicators all along the way of an underlying topological string description, which I think will be ultimately the natural way to view the worldsheet theories. And I mentioned about these correlators in the free n equals to 4 Yang-Mills and the geometric picture of twistors, which seems to capture many aspects of these free correlators. I think there's much more to be done there to flesh it out and to understand these twistor geometry of these twistor incidence relations from the worldsheet perspective. And of course, you would like to perturb away from the lambda equals to 0 and see this integrable spin chain description arise from the worldsheet theory. And it's very encouraging that all the ingredients are there. The bit picture is there, which really is what the building block of the integrable spin picture. And in fact, these twistor variables arise very naturally in the integrability approach to understanding the theory away from lambda equals to 0. And this would give the current picture would give some kind of a covariant worldsheet description of that integrability picture. So that's all, and thank you.
So thank you, Rajesh, for an exceptionally clear talk. And we have a little time for some questions, but before I throw it open to the audience, there is one question from Nabamita in the chat. And 𝗦𝗵𝗶𝗿, could you please ask the question yourself?
Yes. Just 1 minute.
You have echo because 2 devices are on with a microphone.
Okay, sorry for that. So
No,
I just wanted to ask that the operational definition for the proof that Rajesh, you provided in the second slide of yours.
Yeah. Sorry.
Yes, the first equation is. So for well-known examples of ADS CFT that we know, suppose say for ADS 4 CFT3s or ADS 5 CFT4, this is this must be known, right? I mean, for examples that we know, there this relation must be true, right?
So what has been checked is, of course, the left-hand side, you can compute when you can compute. Of course, in the free theory, you can compute, but most of the checks that people have done are for the spectrum, of course, but where you have studied correlators, it has been at strong coupling. So in the opposite regime, where the right-hand side is given by some supergravity on shell amplitude, and then you can check. Of course, there are many cases which are BPS protected and so on, like in the famous n equals to 4, the example itself, Shiraz and others had in the early days itself shown the equality of the 3-point function of BPS states. So there are cases which are either protected by BPS, these things, or through localization, you can compute certain things. So in those cases, people have checked individually, but it is, of course, not known in general why it is true, or even if it is true. I mean, it's very difficult. There's an infinite number of checks here. And certainly no one, I think, has looked beyond 4-point functions.
Yeah. So my question was for those very specific limits, at least this relation is well understood for, say, for n equal to 4 Yang-Mills and the corresponding supergravity theory in the limit.
I mean, it's not understood. The right-hand side is not understood in a worldsheet description, but yes, from a space-time description, it is understood. You have the so-called string field theory, which in this case is just a supergravity theory.
Thank you.
Okay. I think there are some raised hands. The first is Ashok Sen. Ashok, could you please ask your question?
Yeah. So my question is the following: that you described it in the Euclidean version, right?
Yes.
But in the Lorentzian version, people have considered this quantum error correction mode to reconstruct the bulk of ADS. And since you have a free field theory correspondence, I'm wondering whether one can explicitly check that, or is it will it become just tautology?
The free field limit is a bit of a singular limit in that the world sheet is effectively at the boundary. So in a way, the bulk and the boundary distinction itself becomes very fuzzy. It's firstly of string scale. The whole bulk itself is of string scale. And the world sheets that dominate are effectively at the boundary. So the notion of the reconstructing the bulk in a sharp way, when we don't have locality at that scale, the ADS scale is the string scale. So I'm not very sure how it would work.
Okay. See, my understanding is that this bulk reconstruction that people do, I mean, there you do take all scales to be of the same order. Right? Nevertheless, you reconstruct the bulk because you take the overall size, right? Not the curvature is of the order of the string scale, but you just take the overall size to be very large and you construct a local bulk at a scale larger than the ADS scale.
Yeah, but here, how would that be possible? I mean, here the bulk, it's, you're talking of the infinite ADS.
Exactly. I think when people talk about bulk locality, that's what they mean. Because I don't think that they have constructed locality. I mean, they have understood locality beyond the ADS scale. Right. So it seems to be a good testing ground for.
Yeah. So there is a kind of a UVIR, this thing, in the sense that the depth to which it sort of goes in is related to the separation in the boundary of the correlators. And so there may be a way in which you can sort of see how, because the string does probe more of the inside depending on the positions of the insertions on the boundary. And there may be a way to do it, but the picture that I have, at least, of how this bulk would be reconstructed is more like an RG picture, that you have these bits on the boundary, and these bits, like just by integrating out the entanglement between adjacent bits, you're kind of going deeper into the boundary, like this tensor network picture. So there may be something like that, because you have a free theory indeed, and you can just look at the entanglement structure of the spin bits of this free theory and probably see this very explicitly. That is indeed, it is possible, but I haven't thought anything more about it concretely.
Okay, the next question, Sunil Mukhi.
Yeah.
Could you ask your question, please?
Yeah, Rajesh, the conventional wisdom about string theory on ADS5 cross S5 would be that the world sheet theory has a Ramon background, which is difficult to quantize and so on. And it's a large background, right? It's proportional to N. Now you have a free field, an alternate free field description of the same string theory in a limit where lambda goes to 0. So is it sort of a claim that in this limit, or more generally, there's a map from a non-trivial sigma mod, that non-trivial Ramon sigma model to this free theory? Is that somehow one interpretation of what you have done?
Yeah, I mean, it would be very nice to understand the connection to a conventional sigma model description. So the best I can say is that firstly, we are now in a highly curved ADS regime, and in some sense, the Ramon flux is minimal. So at lambda equals to 0, strictly speaking, the Ramon flux in a way doesn't really enter, because Ramon flux enters as G string n, and G string n going to 0 is really a point where you don't have in some sense a Ramon flux, but nevertheless something is stabilizing that background. It's there in some quantum sense, it is there, I think. And that's what I think this level 1 theory is doing, a bit like SU2 level 1 theory does. It's a highly curved sphere, and in fact, it becomes a circle in that limit.
Exactly. It's a map from some very curved manifold to a flat.
To this thing. So
simpler variables.
But here, that's why I feel the underlying geometry is best thought of in the language of the twistor space of ADS5. This is and because that's the interpretation of this free field theory. The free fields are not any old free fields. They have a geometric interpretation as giving the twistor description of ADS5. So, and the twistor correspondence of Penn Penrose allows you to make a correspondence with space-time, but it's a very non-trivial correspondence. So I think anything will have to flesh out this twistor correspondence at the stringy level, any map between these variables and the usual space-time variables.
Okay, there is a question from ICTS. Please go ahead.
Hello.
Yeah, hi, Loga.
Yeah, hi, Rajesh. So in this, I just wanted to ask, in this twistor way of describing this world sheet, like, do we understand how to think about d-branes in the bulk, or the d-branes ending in the boundary theory?
Absolutely. I think, I mean, it's not something I have looked at in any deep sense. In the ADS3 case, actually, Matthias and his collaborators have a paper on the d-branes in the ADS3 case, which in terms of these free field description, the corresponding free field descriptions in ADS3, which actually have a very nice correspondence with the d-branes of the symmetric orbifold theory as well. So I presume something like this must happen here, because this is again a free field theory. You can look at the corresponding d-brane backgrounds. And indeed, I think these are very interesting things, because I think there will be an effective description on the d-branes, which I think should give you the Berkowitz open string theory, the things that Witten and Berkowitz and then Mason, Skinner and all used to describe free Yang-Mills amplitudes using a kind of an open string theory. I think that should tie up with the d-branes in this background. But that is, of course, it's just speculation at them.
Okay, Alok, please ask your question.
Hi, Rajesh. I just have a small question about the incidence relation that you showed in the end.
Yes.
Yeah. So the usual twistor in the Minkowski space, these mu's are constructed simply out of the undotted spinors. Right? I mean, the right-hand side is 0. I was just
Exactly. So this is the twistor incidence relations for ADS5. They're not the same as the incidence relations for Minkowski space. And they reduce to that. In fact, when this is the radial direction. So there is a way in which you can take the limit of the ADS5 incidence relations and recover the incidence relations on the boundary, which are the usual incidence relations. But this is then what you recover on the boundary is the so-called ambitwistor description of the boundary theory. And the ambitwistor description has both dotted and undotted spinors.
I see. And then
subject to an overall ambitwistor constraint, which is the one actually that I was showing you as the C constraint. Yes.
But this solves the second equation that you have. I mean, the one that is written. So the X
exactly.
Yeah. Okay.
Yeah.
Thanks.
Alok Mishra, you have your hand raised.
Yeah, sorry. So I just had a question. So Rajesh, on the, if I remember correctly, in the math community, I think way back in the 80s, probably 88, somebody, I think by the name of Schmidt, so he was exploring a connection between essentially the algebraic geometry of moduli spaces of Riemann surfaces using what was called as, I believe, I think Arkilov's intersection theory, involving determinate line bundles of Riemann surfaces, and this could actually be understood in terms of string partition functions. So I was wondering, is there some interest in the math community to study this duality that you suggest, purely from, let's say, intersection theory in the context of moduli spaces of Riemann surfaces?
Yeah, no, it's interesting you mentioned the Smith's paper. Smith was actually a physicist, theoretic. He was a string theorist by training. He now works in the Shell Corporation. So anyway, but Smith actually tried, as you said, to make sense of the so-called integer points in this moduli space. What he didn't realize at that time was that there's a geometric picture, the mathematically geometric picture to something called the Belly maps, which are precisely these points, which has been fleshed out in the maths literature. And there are people studying these very special points where the Strebel lengths are integers. They correspond to what are called arithmetic Riemann surfaces. And so these are a special set of points on the moduli space, and they begin to densely cover the moduli space as you take these lengths to infinity. It's related to a whole set of very beautiful mathematical results, which I don't have time to go into. But I think there is an interest there from the math side, from their own motivations. They have interest in studying many of these things, and I believe this will give the developments here will give a new angle to that. But of course, one has to communicate to mathematicians and get them in. But I believe it's a very fertile regime for this to happen.
Thank you.
Okay, very good. I think let's thank Rajesh once again for his very lucid talk, and move on to the next session.
Thank you very much.
So now may I invite Chetan Krishnan?
Yes. Okay. So shall I share the screen or?
Yes, please share your screen.
There you go. So
Chetan's title is Comments on Asymptotically Flat Space.
I slightly
go ahead.
Title for the
space-time.
Slightly more concrete title.
Okay, good. Go ahead.
Okay, thank you.
Yeah, please.
So let me start by thanking Spenta and also Alok and his friends for organizing this conference and letting me speak here. So the title of this talk is A New Gauge for Asymptotically Flat Spacetime. So this is some work that I've been doing with Jude during this COVID couple of years. He has been a brilliant collaborator of mine, and he is right now started his PhD at Arizona State, and hopefully 2 papers will appear soon, one of them hopefully in the next few days. So, and it's broadly motivated by some work that I had done some time ago on this thing called asymptotic causal diamonds, which I'll maybe have like a couple of slides about. So, right. So, what was, so the thing I wanted to, so the material is a bit technical. I usually don't like to give too technical talks, but the second half is unfortunately a bit technical. So, but hopefully it is not too painful. And please feel free to ask questions. I don't necessarily have to get to the end of the talk. So the basic setting is that, generally speaking, flat space holography, attempts at flat space holography are usually phrased in Bondi gauge. And I'll show you what Bondi gauge is. Very roughly, for the moment, the only thing we need to know is that it is a coordinate system adapted to the future null infinity of flat space. And despite its many virtues, I will argue in this talk that there exists another gauge which may be, for some purposes, more useful, or at least useful for getting some more hints about what flat space holography is or should be. I mean, I'm not necessarily claiming that this is the final gauge or whatever that is useful, but hopefully it will be useful for extracting some more information than what is accessible in Bondi gauge. And the motivation, there are a bunch of motivations. The first is that the natural observable for flat space holography is the S matrix, which has a natural ties to both past and the future. And Bondi gauge addresses only the future or the past at any, the future Bondi gauge addresses one and the past Bondi gauge addresses another. And the motivations for this, for the choice that Bondi made and Bondi and his friends made long ago, is that they're largely historical, and it's motivated fundamentally from the need to understand gravitational waves back in the day. And they wanted to look at a gauge where you could look at isolated gravitating systems from which gravitational waves were, being detected at infinity. So this whole picture has a kind of a retarded correlator feel to it, and Bondi gauge reflects that. So I think what I will try to present is a gauge which is in some sense has both access to future and past, and in that sense it is more a Feynman-like gauge. So you'll see that it is kind of a double null gauge, and I'll specify what exactly it is in a few slides. So that's our, so continuing on with the motivation. So another reason why this may be of some interest is that Strominger's diagonal BM symmetry that he has identified for this gravitational S matrix, it requires a matching between the future and past, and it crucially involves the future and past. It is not just the future that you need. So What he does is he works with the future Bondi gauge and uses the past Bondi gauge, and then he tries to match them in some way. So what we will do instead is to try and have a gauge where both these things are simultaneously present, and we'll see whether it has some utility or not. So so this is yet another sort of philosophical point is that typically holography, you think of it as defined on codimension 1 screens of some type, and in flat space, if you are using only the future or the past screens, we are using only a part of the codimension screens that are available to us. We would like to have at least a formulation where both are equally accessible. So also, I think I just saw that I'm giving this talk from ISE, and there was some warning that said that the ISE WLAN is a little bit shaky. So please, if you have any, if there is if you cannot hear me, you can call me. I think my collaborator is in the audience. So if I decouple, please just let me know. So I hope you can hear me now, right?
Yes, we can hear you.
So the one more motivation, so to speak, is that the holographic or asymptotic direction is the radial direction in Bondi. So even though the screen is in scribe plus or scribe minus, the way you go to the asymptotic region is along a radial direction. And I think it is more natural to think of these as being approached along a null direction. So that's, let's say, another way to think about it. So another reason to think of it as maybe a motivation for another gauge. And the final thing, which is what I mentioned in my paper from a couple of years ago, where so the idea is that that was my motivations there, where from the point of view of bulk reconstruction or bulk locality or things like that. And so the idea is that just like you have ADS causal wedges from which you can reconstruct things from the boundary, you can attach causal diamonds to the conformal boundary of flat space. These things are, these asymptotic causal diamonds, so to speak, are a natural generalization of ADS causal wedges, and it's a natural starting point for bulk reconstruction in flat space. And the space of ACDs is defined by a pair of points on scribe plus and scribe minus. So if you have a point on scribe plus and scribe minus, you can, or if you have a point on scribe, in the 2 points on the boundary of ADS, which is basically 2 points on the boundary Minkowski space, then a causal diamond is defined on the boundary Minkowski space. Analogously, you can also construct, and then this boundary causal diamond can be used for reconstructing the bulk causal wedge. That's the picture that you have in ADS. So here, on the other hand, the boundary is, it has more interesting structure because it's null and everything. But if you have 2 points on the future and past, you can do almost all the things that you can do as far as bulk reconstruction is considered by constructing these asymptotic causal diamonds. So I'll just draw a quick picture here. This is not sort of my main take on this main line of development in this talk, but I just wanted to draw a quick picture here to give you a rough idea of what these are. So this is basically one of the vertices of the causal diamond, asymptotic causal diamond, and this is another one. So, and it's in 1 + 1D, it's completely easy to see what it is, and in 1 + 1D, it also happens to be trivial. But in higher dimension, it has more juice because once you send the causal diamond to infinities, the boundary structure actually becomes quite interesting and intricate. I won't have much to talk about it today, but this is another reason that I'm thinking about future and past simultaneously. Okay, so and just to go ahead with this a bit, so the reason why these ACDs are not just a simple adaptation of bulk causal wedges in ADS is so there are few, the way in which these things work out in flat space is not entirely trivial, or at least I think it is not entirely trivial. There are some subtleties, but still it works out many of the things, and there are some cases, some things which are substantively different. So but the point is that if it has a natural interpretation of this kinematic space for flat space holography in the same sense that these boundary causal diamonds were viewed as the kinematic space for ADS-CFT. So these things have precisely the same structures in many ways. And if you also have a bulk screen, you can define regions on these screens which satisfy many of the properties of entanglement entropy and quantum error correction and various other simple and nice things. So all of those things very easily work out. And so again, I mean, this is just as broad motivation for why I think it is interesting or important to consider both the future and past simultaneously. And I will show you one picture from a paper that I wrote with Jude and another junior student, Vaishnavi, of mine, And the only reason I'm showing you this picture is because compared to this is significantly more beautiful. And that's one of the strengths of, working with junior collaborators. And this is, so this thing here, so this is in the conformal coordinates, this picture. So this thing that you see at the edge here is actually the picture of a asymptotic causal diamond. And this blue line that you see here, this is actually it's a straight line in Minkowski space, and that's the waist of the causal diamond. Okay, so it's just that because it is conformal coordinates, it looks good here, but it's really the same thing. And if there is matter inside, you can actually show that this quantum extremal surfaces, etc., are perfectly well defined, and they get pulled in because of gravity, just like they do in ADS. So all of these, we wrote this in the context of this page curve discussion. And so you can argue for the existence of phase transitions and all that kind of thing in this context. So anyway, so this is all largely just motivation for why it is perhaps reasonable or interesting to consider future and past Scri plus and Scri minus in flat space seriously, if we want to think about holography in some sense, or at least it may be of some use. Okay, so that's basically the general motivation. Now I'm going to go and talk about the actual stuff. I'll pause for a second and take any questions if anybody has anything to ask. Okay, so so if there are no questions, so the basic idea is just that first we try to look for a double null coordinate system, and you can justify it in somewhat more fancy ways, but it's kind of should be intuitively clear that a double null coordinate system will simply have this gauge imposed on it. So, but the point about double null coordinates is that they're not a complete characterization of a coordinate system, because there are just two conditions in a space-time with many coordinates. So you need to choose one more set of enough number of more conditions so that you actually have a perfect, well-defined gauge. And the thing that we will choose, because we want to sort of retain the symmetry between the future and past, is we'll set GUA is equal to GVA. And this is what we'll call the special double null gauge. And just to contrast with Bondi, if you're familiar with the Bondi gauge, Bondi gauge is basically something like this. Okay, so this is the definition of Bondi gauge, and this is only 3 conditions in 4 dimensions. So they also impose a determinant condition. Note that our condition, because this is 2 conditions, A is the coordinates on the sphere, and these are 2 conditions. This is equal to 0 and this is equal to 0. So altogether, we already have 4 conditions. Okay, so this is the 4 conditions are already imposed. Here, on the other hand, you also need the determinant condition on the sphere metric in order to get some traction. Okay, so one way in which one particular ansatz, or you can write this is a metric that one can write down which satisfies this gauge. Okay, or there is enough number of functions here. So this omega AB has so there are two components for this. Then there is 3 components, 3 or 2 plus 3. This is 2 plus 3, 5 plus 1. Yeah, this is correct. So there are 3 components here. There is 1 component here, and then there is 2 components here. So there are 6 coordinates here. And similarly for Bondi, you have 1 function here, 1 function here. This is 2, and then there is 2 here, and then 2 here. So that looks like it is 2 plus. No, this is 3 and 2 and 2. This is 7. But then there is a determinant condition on this metric of this omega AB. So you end up finding that it's actually 6 as you would like. So there are 6 functions worth of 6 functions here. So that's basically our gauge, and this is the setting in which we are going to work. Okay. So note that we have done nothing so far. All we have done is process some coordinates. There is nothing about flat space. There's nothing about anything here. It's just a coordinate system for writing any metric that you might like in 4 dimensions. So so the first thing we would look at is that so let me just flash you. So yeah, so I wanted to just look at, this is Minkowski space in double null gauge, if you like. So in Minkowski gauge written in double null gauge, we can we can find out the asymptotic action of the Poincare transformations, and for Poincare transformations in the boundary of this flat space. And it turns out to be, it's somewhat similar to what one does in the case of Bondi gauge, and you find that the translations act like this, and the boosts and the rotations act like this. Okay, so this is just something that you can figure out. And so the question, so I mean, in some sense, the big question in my mind is that are there any interesting unitary theories that live on this 𝗧 plus union 𝗧 minus, they are the Poincaré acts in this way, because an action of Poincaré is quite nice in some way. So maybe there is a way in which you can just use this if you have enough imagination to guess the kind of theories that are going to be interesting on this pair of spaces. So I mean, it may not be the best way to formulate this might be to go to analytically continue in some way or something like that. But I'm saying that this is if you have an interesting answer to this question, I think we are quite a ways to understanding what it's the analog of knowing what a CFT is in the context of ADS CFT, I would think. So yes, so that's the thing. But of course, it is probably too ambitious. And our goal in this talk is, in some sense, much less ambitious. So I flashed this slide too fast, probably, but it's it's just there's nothing to there. It is just the asymptotic action of Poincaré on these coordinates, and you can just believe me that those things are, you can figure them out, and yeah, the slides are there. So yes, and so our goal in this thing is. So what we would like to understand is we want to understand the asymptotic behavior in the special double null gauge of our metric, and we would like to solve Einstein's equations, etc., asymptotically, figure out BMS or something other symmetries. These are our broader goals. So, and we try an expansion of this form. Okay, so these are some of the metric functions. I mean, there are others. So 2 of them I'm writing here. So, and these are the fall-offs that you have. So, well, this gamma ZZ is actually 0. Because the sphere metric is, ZZ, it only has support on gamma and ZZ bar, but I'm just writing it for illustration. So, so this is the kind of fall-offs that one can try. And so the first thing we can note is that because we are working in U and V coordinate, our holographic direction is null. Okay, so we are going to 𝗧 plus, but not along R. And clearly a similar expansion can be done in the past direction as well by doing an expansion in 1 over U. Okay, so this may be seen similar to the past Bondi gauge, and this, morally it is similar to past Bondi gauge, but there's a crucial distinction, which is that in Bondi gauge, and the gauge I'm putting in quotes because there are really 2 separate gauges in the future and past, and here we only have 1 gauge, and what we are really doing is we are doing 2 expansions for the same gauge at 2 boundaries of spacetime. So the future boundary of the 𝗧 plus and the past boundary which is 𝗧 minus. So we have only 1 gauge, and we are doing 2 expansions and 2 boundaries, as opposed to a Bondi gauge where there is a future Bondi gauge and a past Bondi gauge, which are 2 different gauges. All right, so that's one thing. And so now we start systematically imposing. Our goal is to see what the asymptotic symmetries are, whether we can make connections with the things that are already known in Bondi gauge or Stecker-Hansen or any of the other gauges. That's our goal. So to impose asymptotic flatness, so asymptotic flatness here means asymptotically Minkowski, and so we can start by checking what happens if we demand Riemann is equal to 0. Okay, because Riemann, so oftentimes this is phrased as a statement that Weil tensor vanishes at the boundary of spacetime, but that's largely because of the fact that Riemann contains Ricci and Weil. So if you demand Einstein's flatness, Einstein or Ricci flatness, then all that is left is the Weil. So this is, you can think of this as the equivalent of sometimes in the Bondi context, people will talk about the Weil curvature vanishing in some ways. So yeah, so we are going to demand this, and so yeah, so one may be forgiven for thinking that this would force us into the form of Minkowski space in our gauge, where we write U is T minus R and V is T plus R. Okay, so if you just demand Riemann flatness, you would think that you would get Minkowski space back. But that is not quite what happens. Note that we are imposing it asymptotically in this sort of a fall-off, and this is not what happens. What happens instead is that this Riemann flatness allows a whole towers of undetermined integration constants that are purely functions of the angle Z and Z bar in the fall-off coefficients. So what I mean to say is that these coefficients here, they still allow the possibility of arbitrary, not all of them, but 3 towers of them, basically. 3 towers of them allow integration constants that are, I call them constants, but they are functions of the angle Z and Z bar. So that's what Riemann flatness fixes for you. There are some systematic exceptions, as I said, but this does not affect our story, so we will not emphasize them in this talk. And in fact, these integration constants persist even when we solve the Einstein equations asymptotically. So one way in which this manifests itself is that unlike in Bondi gauge, here the Einstein's equations typically only determine the U derivative of the fall-off coefficients. They don't determine them algebraically to higher and higher order. Typically, Einstein's equations, if you have some integration data and you put something, so if you prescribe enough integration data, what happens is that it will fix it to all orders. But that's not what happens here. What happens here is that as you go to higher and higher orders, you keep generating these integration constants, which are functions of just the z and the z bar. So the fact that they show up even when we demand Riemann flatness is a hint that these are trivial gauge parameters, which can be set to 0 by trivial diffeomorphisms. Okay. In fact,
there is a question, Chetan. There is a question from Isa Bhopal. Would you like to take it?
Yes, please go ahead. Yeah.
Go ahead.
Hi, Chetan.
Hi.
Am I audible?
I can hear you, but I think a little louder may be better.
Okay. Can you just go back a few slides?
Sure. Here?
Yeah, sir. So here the expansion you are only writing in terms of V. So
I'm writing in terms of U. So I'm going in the direction of V. V is the holographic direction here. I'm going to V infinity. So which is future infinity, Sky plus. And my coefficients are arbitrary functions of U, Z, and Z bar.
Okay, and so is like that at any point you would also like to know how it behaves with you or not?
Sorry, I can't hear you.
Will you also like to know how it behaves with you or?
Yes. So I will also look at what happens in past null infinity. So I will also look at what happens in past null infinity, and here I'm just looking at future null infinity. I'm expanding along the future direction and doing things, but I can also do it along the past direction by expanding along U and going to minus infinity. Yes, I can do it. And in fact, I will do it.
Oh, okay, thank you.
Yeah. So yes. So the fact that even demanding Riemann flatness leaves you with these trivial gauge parameters, I think we'll find multiple pieces of evidence that this is an indication that these are trivial gauge parameters. And one of them is the fact that Riemann flatness just leaves you with this. Okay. And in fact, we discovered it actually by, as a contradiction of 𝗏𝗀𝗃𝗀's theorem. So we were trying to find what happens in Schwarzschild. What is the analog of the sterically symmetric vacuum solution in flat space? And we ended up finding these parameters and we were confused. So these trivial functions which were confusing. So in the end, it turns out that even if you demand Riemann flatness, you find these, and these are trivial gauge parameters. And so one way to get some confidence in this, and this is a slightly technical way to do it, and only the result is important to us, so you can find it in our paper if you want, is that in Einstein gravity, you can explicitly compute these surface charges. These are things that Iron Wald and various other people have defined. And we can plug our expressions into their formalism, and you find that these parameters do not show up in the asymptotic charges one defines. And so that's one reason to think that they're trivial gauge parameters. I'll have more to say about them in the few slides. But for now, with some minor choices analogous to some of the choices in Bondi gauge, these integration constants that correspond to physical data. Okay, so there are so the way, when you do this solve Einstein's equations, what do you call it? When you solve Einstein's equations, asymptotically, you find data analogous to what you find in Bondi gauge. And in fact, apart from these trivial integration constants that I talked about, there is also data of this form. Okay, so these are the data that we have. And these are analogous to the shear data, the mass aspect, and the two angular momentum aspect data. Okay, so these are the things that one has. And we can also define a news in the same way that essentially the same way that one defines it. So this lambda shows lambda2 is a second coefficient in the expansion of the lambda field, and alpha is the thing that is there in this here. So this is the alpha. So I have some expansion for omega, some expansion for lambda, and some expansion for alpha A. So the omega AB expansion is one of the terms in that is basically what this shear is. And the lambda is one of them is this, and this is the quantity that shows up in the angular momentum aspect. Okay, so to give a flavor of some of this, let us write down the Einstein constraint on the mass aspect, which happens to be quite simple. And this has some structural similarity to the Bondi mass aspect constraint as well. One crucial difference is that what we have is a second derivative, and this is consistent with what I was saying before about we always seem to be getting these extra trivial integration constants on top of all this. So, and a similar but more complicated expression can be written for the angular momentum aspect as well. Okay, so and yeah, so that's basically that. I'll come back. I'll have more to say about these things if I get to the end. So the point is that asymptotic symmetry. So the thing that we would like to compute, the standard thing that we would like to compute, is asymptotic symmetries and BMS. And this is somewhat of a technical enterprise. Yeah, so but the conclusion is, in some sense, but it's quite straightforward. There is nothing particularly, it's like you just follow the formalism or the calculations that Bar-Nish and Troissart have done in the case of Bondi gauge, and we can straightforwardly adapt it to our situation and try to do the calculations. And you find that these asymptotic killing vectors that were defined. So the asymptotic killing vectors are basically solutions to L psi g mu nu equal to some order fall off, and the choice of the fall offs is where the sort of the game is. And well, I mean, actually, in our case, it is actually fairly straightforward once you play around with it. But and you find that once you choose a set of fall offs, you basically find that the killing vectors that you're left with basically have some amount of freedom, and these freedoms are what are basically called super translations and super rotations. And you can define a sort of a commutator of these things, and you have to, there are commutators and there are some modified commutators, etc., that one has to define. And once you compute all of those things, we find that even though the details in which the calculations arrange themselves is quite different, at the end we have precisely the same information as what happened in the case of Bondi gauge and so on. So one can think of that as either encouraging or disappointing, because if you're hoping to find that you're hoping to find something more, maybe this is not finding BMS again may not be the greatest thing. But there is one interesting point, which is again related to these trivial integration data.
So,
sorry,
Chetan,
yes.
Before you go on to that point,
yeah,
Alok Lada had a
yes.
question.
Chetan, hi. I
Yeah.
just had a small question that since you did not fix the sphere metric, right, at infinity.
Yeah.
So that,
I think, in this choice, when I'm saying it here, I'm fixing the sphere metric.
Okay, because the news, otherwise the definition of news is not, you have to add the extra term.
But we have a discussion of the more general case also in the paper. So what actually happens is that in the double null gauge, the sphere so I mean, it just becomes, the freedom that you have just becomes a function of Z and Z bar. It turns out to be the case. We have not fully understood why that happens, but But in that freedom, I mean, the definition of news in general is not 12, but there's extra term. There is the right. So this is here I'm fixing it to be gamma ZZ bar, which is the sphere metric on this thing. So this is, I'm trying to be as close to BMS here.
Okay, thanks.
So, and also, so there are a couple of more comments. I think, maybe you can, I can tell you at the end. So there is so there is a question about log fall offs that one has to worry about, because, one might worry that, so typically in a Schwarzschild, if you write in Eddington-Finkelstein or something like that, you actually find that there are log terms that show up, right? So, but we have not introduced any of them. We are kind of expanding in 1 over V, but we're working with, so this looks like we are assuming, we are working with an analytic expansion at infinity. So is that allowed is a question that one could ask. But it turns out that there is an interesting resolution of that because of the presence of these trivial integration constants. But yeah,
and large positive V, right? You're expanding at large positive
large positive V, that's right. Yeah, large positive V, and I'll also do that in the large negative U. So yeah, so the one difference in the when we get the BMS algebra is that unlike in Bondi gauge, together with super translation, super rotations, these asymptotic killing vectors come with an infinite towers of unfixed trivial diffeomorphisms, which are precisely in one-to-one correspondence with the trivial integrations that we saw when we are doing the follows. Okay, and so one can explicitly show that these trivial AKB coefficients have precisely enough freedom to set the corresponding trivial gauge parameter to 0 if we choose. And this can be, so this can be seen by first determining the action. That's a technical comment. So it's just true that, AKV coefficients, which are these infinite towers of these trivial AKV coefficients that show up, can be one-to-one mapped to the trivial gauge parameters, which is another reason to think that, to be, convinced that they are just trivial diffeomorphisms.
Chetan, how long will you take now?
I think my real number of slides is still 30. So I think that I can wrap it up in another, can I go to 11:30? Is that okay?
11:30?
It's 11:18 now. if I have 11:30, I can. So yeah, I mean, okay. I mean,
okay.
How much more?
Try to do it in 5 minutes.
Okay, sure, I'll try.
All right.
So, so yes. So then there is a second question is a similar discussion for 𝗦+ applies also to the past. And so in order to define a classical scattering problem, we need to match the integration constants at 𝗦+ and 𝗦- across I0. This is sort of the future past antipodal matching of Strominger that we have. But there's a natural way to do that in our case, which is that we basically demand asymptotic CPT invariance on all solutions. And the asymptotic CPT invariance basically acts like this. And so that lets us match these integration constants. So I'm writing this C and C tilde. So C is for the future integration constants and or the data, and the past is for the the one in the past. So they have to be matched in this way. And so the reason why sometimes in the case of standard BMS discussions, people often match it as C z bar is equal to C tilde of Z and Z bar. And the reason for that is that because they have two different coordinates in future and past, so the Z that is defined in the past is actually with respect to the south pole. So that's where they don't have to do this inversion. In our case, we do have to do. We have only one coordinate system, which is this gauge, and so because of which this is the mapping that we have. So I want to emphasize that it is not an extra complication. It's just that the extra complication is not visible when you work with two different coordinate systems in the case of bonding. Okay, yeah. So this is not very important. So yeah, so let me come to the so the general structure of when we integrate these constraints is that we have so the general. So I'm just writing a schematic expression for a general constraint, how the Einstein constraint gets solved. So what happens is that when you do something like this, so the general solution is you have an integration from 𝗦+ up to U, and so you have, so this is some, so this is the right hand side of the constraint, whatever that might be, and this is the general form that it takes. And we can demand that the integral here converges at the lower end. That's one way in which, for instance, in the case of the Bondi mass aspect, sometimes this fall-offs called these Christodoulou-Kleinerman fall-offs are often invoked. And so, I mean, at least in the Bondi mass aspect, this argument works. And you say that, okay, this integral has to converge, and that, the fall-offs that Christodoulou and Kleinerman suggested would accomplish that. And then you have this, then this is basically the, this is the, these are the two pieces of data that you have. So, but I think that in our, I think that it may be it may be more interesting or more useful or probably more generally valid to consider the possibility that in this integration, which is happening at spatial infinity, 𝗦+-, okay, so it's close to spatial infinity, to put a cutoff here, and then if you have a cutoff here, the whatever is the divergence or whatever it is, that you can absorb into this trivial integration or the integration constant that you have sitting here. So, and I think that it is this renormalized integration constant that should really be matched between future and past. And the contribution from the lower end of the integrand can then be simply viewed as renormalizing the bare integration constants. And I think that the fact that this is the structure that universally shows up in our gauge, I think is, I think it is very suggestive in some sense. And I think that this is probably this structure, I think may be of some use in understanding flat space holography. Note that this is basically a light ray-like integral. Okay, so I think that's, I think I'll go, I can say a little bit more about that, but let me go to the sort of the concluding couple of slides. So, so yeah, so the basic message is that it may be useful to think of 𝗦+ and 𝗦- together as a natural habitat of the hologram of flat space, or maybe it's some sort of analytic continuation of it. And can we find an interesting unitary theory there where Poincaré BMS act in the way that we have described? So, so the quick question is, what are the natural operators? If you want, if you want to push this in some ways, what is the natural operators that might live there? And so one natural guess is this light ray operators, light ray-like operators that I mentioned here. Okay, so these things are somehow living in I0, if you want. Well, it's not clear where they live. It's basically just it has only angle dependence. So, and but the point is that these integrals are from past null infinity on the 𝗦+ to some specific point on 𝗦+. Okay, so these are sort of light ray-like operators, which are integrated between some point on Scri plus to spatial infinity. So on the null generators of Scri. So, and they seem like natural candidates for various purposes. And what happens if we solve, so one of the things that we have not done completely yet is that, the first thing to do is first solve Einstein instead of trying to solve scalar field theory. So what happens if we solve free scalar field theory in Minkowski space in double null gauge? So, and this is something that I'm doing with my student, 𝗦𝗫𝗀𝗃𝗃, who's probably in the audience. And an object called the Riemann green function naturally incorporates some of the structures that shows up in the case of Einstein. So, and I have a suspicion that the holographic data that is captured by this, note that this is entirely holographic data. This is purely on the boundary, the Scri. Okay, so, and can we view this holographic data as analog of some form of normalizable and non-normalizable modes in ADS or some such way of, exhibiting that. So I'll stop there, but I have a few more slides. If there are any questions, I can answer them. Thank you.
Okay, thanks, Chetan. 𝗦𝗵𝗶𝗶 has a question.
Yes.
𝗦𝗵𝗶𝗶, could you please? 𝗦𝗵𝗶𝗶?
Maybe she already asked the question.
No, no. No, not really. There is a question in the chat. Maybe I'll read it out.
Please.
Is it not expected that the symmetry will be same as finally you will have U, Z, and Z bar where transformations will work? That's a good question.
What is it? Sorry. What is
that was the question. It's in the chat actually. Is it not expected that the symmetry will be the same?
Yes, it is the answer. The fact that it is BMS. I mean, if you find something other than BMS, or if it is something smaller than BMS, then I think it clearly means that something is wrong. At least we should find BMS, and we do.
Okay.
So the question is, but we have tried to adjust our, we have not worked with as general as a expansion as one can have. So we could try more general, so there are some minor choices that we have made, as I mentioned here, so that we are not working with some, so we first wanted to kind of establish that we have some common ground with the BMS literature. So in order to do that, we made some guesses, or not guesses. I mean, it's like there are, for instance, we have worked with we have not allowed, as Alok was saying, that we have not allowed the possibility of an arbitrary conformal factor on the sphere. So those kinds of simplifications. So those kinds of simplifications, we expect they will not lose BMS. So we made those simplifications. But there are only two or three such simplifications. And once you do that, you get BMS. So that's kind of the sort of the starting ground. So in that sense, yes. I mean, we have engineered. We have not. Engineered is too strong a word. So we have chosen our, sort of the. We could work with more general these things and expect to find probably bigger symmetries, but it remains to be seen.
𝗦𝗵𝗶𝗶, is that, would you like to say something? Because you were not audible.
No, Sweta, it's okay. I heard what Chetan said.
Yeah.
So I was just, okay, thanks.
Yeah.
Okay. So let me go to there are a couple of more questions. So let me invite Shiraz to ask this question. Shiraz?
Yes.
Hi, Chetan. A couple of quick things. Right at the beginning of your talk, you talked about these Ryu-Takanagi kind of surfaces that ended at Scri plus and Scri minus.
Yeah.
So in your picture, these surfaces compute the entanglement entropy of what with what?
So
is it one part of part of the sphere with the other part of the sphere, or yeah?
So I think it is first. Let me talk about that in the case of Minkowski space. So if in Minkowski space, if you're constructing the base of these causal diamonds will intersect finite radius screens. So, and that's one way in which you can define subregions on the screen. So, and the claim is that the minimal surface that connects these minimal surface or RT surface, whatever that connects the boundaries of those subregions are basically measuring, if so they satisfy things like strong subadditivity or any of the holographic entanglement inequalities. So that's the reason why I'm thinking that they're capturing, so the properties that they capture are precisely the properties that one would expect from tensor factors of theories. So that's the reason why I'm thinking that they are entanglement entropies.
Sorry, I didn't understand. Are they entangling one region of one part of the sphere with another part of the sphere?
So the what is entangling, I think it is a risky question. I think I would not to answer it yet. So what I would say is that these minimal surface areas that they compute satisfy properties of entanglement entropy. That's all I'm saying. So that's the sense in which, which I think it is some sort of coarse-grained entropy where the scale of coarse graining is defined by the size of the screen. I think that's what they're ultimately computing, but a precise definition we don't have. So the point is that, but they satisfy these properties of entanglement entropy. All these holographic strong subadditivity, I don't know. Now I forget. It's a couple of years now. So that's all. I mean, it's not a stronger statement than that.
Okay, thank you. Spencer, do I have time for one more? Or do you need to move on?
Yes, please. Okay. Go ahead.
Again, I apologize if I didn't understand correctly, but when you talked about the mass constraint equation, you had a term with a second derivative of u.
Right.
Now, the way I understand that mass constraint equation is that the change in mass is measured by the radiation that goes out.
Right.
And if that understanding is correct, it's like a first derivative thing, right? Its change is equal to something. So I couldn't understand why you got second derivative. Or is the integral of lambda2 the mass?
The integral of
is lambda2 the mass, or is
no? It's du lambda2, which is more.
Then I don't have a question. Then it's just a derivative of mass is equal to.
Yeah.
Okay, thank you.
So the extra term that shows up is what I was calling a trivial integration.
Thank you. Yes.
Yeah. Okay, Amitabh. Would you like to ask your question?
Yes. Hi, Chetan.
Hey, how are you?
Yeah, fine. So, Chetan, your coordinates cover spatial infinity also because you have both u and v.
I think so. Yeah, but I don't have. These are things which probably you guys know better. I think so. I don't know how to think of. For instance, time like infinity. I don't know what to say about it.
No, not the time like. It's spatial infinity only.
Okay, go ahead. Yeah.
So you have super rotations at null infinity, both u and v. You think?
Yes, I do. Yes.
So you think you will have super rotations at space infinity also?
So we started out with something like Ashtekar-Hansen, but I have not really tried to relate them. We need to do a asymptotic coordinate transformation to connect it to this thing. So I don't have a very strong opinion on it. But one thing I would say is that our coordinate system seems to automatically tie also to because of this kind of equations that I was mentioning. So this kind of equations, this is the structure that one often sees. So and that seems like this integral at minus infinity is basically an integral that starts at I0. So there is something about I0 that is intrinsically built into this formalism. So even though we are looking at future and past gauge. So I don't have a clear answer. I don't know basically. Yeah.
Thanks.
Okay. Alok.
Yeah, Chetan, hi. Yeah, so just one small question, actually related to what Amitabh is asking. So when you do, you use Cry plus Cry minus, but naively when we do conformal compactification with these double null coordinates, we get these Penrose's boundaries, right? So where the Cry plus Cry minus are really touching at a point I0. So there, we never get like disconnected, as far as I know, in this conformal compactification with the coordinates you use, disconnected Cry plus Cry minus, right? And
but I'm not saying that they're disconnected, right? I'm in fact matching them across this.
But they're connected at I0. And what is I0 for you? Is it a point or a sphere?
It's a point.
But if it's a point, then I guess.
I think that's the reason. So I think that's the reason why I'm saying that it's better to probably think of this minus infinity here as being regulated in some way.
Right. So it's different than Bondi, I'm saying, where if you blow up I0 also, you get a hyperboloid which is smooth, right? You are getting these Penrose boundaries, which are really, it's not quite Scry the way we say Scry in Bondi. That's all I'm saying.
Oh, I see. Okay, that's an interesting point. I didn't know that distinction actually. Okay, yeah.
Thanks.
So maybe I'll talk to you. Yeah, that's So that might explain some of these things actually. I see.
Thanks.
Yeah.
Okay, we'll take the last question now from Rita. Please go ahead and ask your question.
Yeah. Okay. Hi. Yeah. Thanks for the talk. So these trivial gauge parameters that you mentioned, like demanding the Riemann flatness, that you get it at asymptotic infinity. Since they are function of Z and Z bar, you said, so you will need probably large gauge transformations to make them zero, right?
Yeah, these are these are asymptotic large gauge they are transformations at boundary, right?
Yeah, so then like setting them to zero, wouldn't that change like the take you from one asymptotic flat solution to another?
So but their charge is zero. So that's one of the things that I mentioned here, somewhere here. Yeah, so if you compute their charges, they are zero. So they don't contribute, they don't come up in the charges. So that's the sense in which they're So that's basically the asymptotic symmetry group, right? So you have this large gauge transformations modeled out by these trivial gauge transformations. So these are trivial gauge transformations. And I think the reason why I think your question comes up is because I think in most cases, for instance, in standard Bondi gauge, you actually, even though we say that there is trivial gauge transformations, like the trivial gauge transformations just aren't there. So when you write down you just say that they don't arise at all. So it's the entire set is just the super translations and super rotations in Bondi gauge. Here, but on the gauge, we have the trivial gauge transformations, and they are going away at the end.
Okay. Thank you.
Okay, so let's thank Chetan again for a very interesting talk.
Thank you.
And now we move on to yes, please stop sharing. Alok Mishra has said that we should have a group photograph. So Alok, may I ask you to take over the proceedings from now on?
Right, thanks a lot, Spenta. So may I ask all of us to kindly turn on our cameras if we feel okay with it, and maybe we can go ahead and have a group photos. So I'm going to be taking screenshots. There are, as of now, 4, I don't know what to call them, sets of participants, 4 screens, 4 whatever screens. I got to score right. So here we go. So this is set 1. Okay, this is set 2, window 2. I move on to window 3. So that's mostly, in fact, all cameras turn off. Anyways, and the last set 4, again, all cameras turned off. Okay, so thank you so much.
I want to wait for a minute before people to turn on.
Acha.
I think now there are some more in the last, anyway, yeah.
Okay, so, okay, I don't mind. So you guys, is it okay if I go one more time for screens, one after the other?
Yes,
one last time.
That's fine. Yeah.
Okay, here we go. So this is 1. This is 2, again. Yes, indeed, Rajesh was right. 3 again. No, 4 not so much, but all the same. Okay, thank you so much. Thank you so much. Now, I have a very humble submission, which I would very humbly ask you to agree, which is that we are running behind schedule. So this is a virtual thing, right? So, we can, if we wish, have our teas or coffees or whatever we want in a shorter period of time. So is it okay if we reconvene 11:45?
Yeah, I think that's really good. I think we should do that.
All right. Okay. Thank you. Thank you. So I'm assuming Sunil is speaking for all of us. So I think we are going to be. So Shiroman, you're on board, right? Shiroman?
Yeah.
Cool. So Shiroman is here, and he's kindly agreed to stick around for the entire the 15 or minus certain number of minutes worth of so-called tea break. So we're going to reconvene sharp 11:45 on the same link. Everything remains the same. Pre-lunch, post-lunch is a different set of Zoom and YouTube links. So I think, and please, another request is that the website of ISM is like a creature of its own, and it gets updated literally in real time by this amazing team of students. So if you want the most updated information about anything, just go to the website. You don't need to ask anybody. If you see it on the website, that's the final word. Okay, that's the final set of links. So we reconvene. Of course, please feel absolutely free to stick around. And so the next talk is, so 𝗬𝗪𝗶𝗶 is going to be chairing the next session. And so he'll take over at 11:45. So cheers. See you then. So folks, Shiroman, are you there? Yes.
Yeah.
So, well, it is 11:45, so it's so I leave it entirely to your discretion what to do, when to do, how to do. You're the boss. So
okay, we'll just wait one minute, I guess. And
yeah,
just...
sure, please. Feel absolutely free. Yeah, thank you so much. Thank you.
Okay, so I guess we can begin. So welcome to the second pre-lunch session. Our next speaker is Anshuman Maharana from HRI, and he will speak about some studies in string phenomenology, and it's a 30-minute talk.
Okay.
So begin.
Thank you, Shiroman. I'll first share my screen. Okay, so should I start?
Yeah, please begin.
So I'd like to begin by thanking the organizers and the team at IIT Roorkee for putting this conference up. And I'll describe work which is done in collaboration with 𝗬𝗪𝗶𝗶, 𝗦𝗵𝗶𝗶𝗶, Matteo Lacheri, Ratul Mahanta, Francesco Muia, Kajol Singh, and Kuber Sinha. So as the title indicates, this talk is going to be based on various recent work in string phenomenology. And string phenomenology has two aspects: the study of string compactifications, and the second, exploration of their phenomenology. And I'll touch upon both. So on string compactifications, we will look at certain systematics of explicit construction of flux vacua. There, we will find some novel solutions with n equals to 2 supersymmetry. We will also look at some flux vacua which are particularly suited for obtaining de Sitter minima. On the phenomenological side, I will look at the evolution of cosmological inhomogeneities. We know by now that there's a lot of interesting structure in the inhomogeneities in the universe. And I will present a scenario where these inhomogeneities can grow very fast, and they'll have some implications. Okay. Now, since I'm talking to a broad audience, let me start with some motivation for flux compactifications. The simplest string compactifications are the ones in which the stress tensors for the matter fields vanish. And these are the Calabi-Yau compactifications. But they have a drawback. They contain massless 4D fields, massless 4D fields in their spectrum, which are called moduli. And they mediate long-range forces of gravitational strength, which are in direct contradiction with the observations. So we need to look at more general compactifications, and this is where flux compactifications come in. And flux compactifications are compactifications in which the antisymmetric far fields that are there in the 10D supergravity actions, they have a non-trivial vacuum expectation values. And once one looks at these flux compactifications, many of the moduli fields become massive, and this is what makes them attractive to when one tries to connect to particle physics and cosmology. And more generally, detailed studies of flux compactification is a natural direction if we want to enlarge our understanding of the backgrounds that we can do string theory in. Okay, so my discussion will be set in type 2B. So let me gather some essentials for that. Here, the internal manifold is conformal to an orientifolded Calabi-Yau that I will denote by X. And the light degrees of freedom are the complex structure and Kähler moduli associated with the Calabi-Yau. Now, the effect of turning on fluxes in the 4D effective action, it is captured by a superpotential. It's known as the flux superpotential, and it is the integral of G3 wedge omega over X, where F and H are the three form fields of type 2b, tau is the complexified dilaton, and omega is the holomorphic three form of the Calabi. And the forms, they thread the three cycles, and this leads to a potential for the complex structure and dilaton. Importantly for the fluxes, they satisfy Dirac quantization conditions, and hence their integrals over the three cycles are quantized. And they also have to satisfy a tadpole condition. That is the integral of F wedge H over X that is bounded by something that's called 2 times QD3, and that's the net negative D3 charge in the internal manifold. So that arises from O3 planes or racked D7 planes. Now, the above two implies that when we're looking for flux compactifications with specific properties, we have to solve Diophantine equations. So these are equations in integers, we have to solve this. Now, there are various aspects of this superpotential that are interesting. I will focus on flat directions or approximately flat directions in the flux superpotential, and that's based on these two papers. So why approximately flat directions or flat directions? Well, by now it's known that this is a generic feature when the number of moduli is large, as was pointed out by these 4 authors and later on by later on in various follow-ups. And they're also interesting from the point of phenomenology. You need an approximately flat direction for inflation. And as we will see, they also can be very useful in constructing de Sitter vacuum. And also they lead us to interesting solutions of type 2b supergravity in their own right. So let me begin by describing this work, which will appear soon. So what we do there is we analyze the types of condition between W and derivatives that can lead to a residual moduli space. Because if you have an approximate flat direction or a flat direction, you need a residual moduli. You are having a residual moduli space, and that implies some conditions between W and its derivatives. And imposing these conditions actually leads to simplifications in the Diophantine equations. And this allows us to find explicit solutions for the flux quantum numbers and the residual moduli space. So we have a good understanding of this vacuum. So instead of going through the general analysis that we do in the paper, I will go by examples. The first is about some novel solutions with n equals to 2 supersymmetry that we find. So the simplest relationship that one can think between the superpotential and its derivatives is a linear relationship. And that leads us to Ворк-Minkowski flux compactifications with n equals to 2 supersymmetry on toroidal backgrounds. And interestingly, one can also make the choice of fluxes such that the dilaton is unfixed. So you actually have a flat direction along the dilaton. So this combination is novel, having n equals to 2 supersymmetry and a flat direction. And so we hope that this extended supersymmetry and the possibility to tune the dilaton makes these solutions ideal starting point for improving our understanding of flux compactifications. And this should be interesting from other points of view. I mean, a question that many people are interested in is what are the kinds of n=2 compactifications that we can get from string theory? And it's easier to understand n=2 compactifications. So we've got these n=2 compactifications that we plan to study in detail. They should also be relevant for this classical Rajesh growth conjecture. Now let me move to the next topic, and that's related to the expectation value of the flux superpotential, which is called W0. Okay. And W0 much less than 1, its magnitude being much less than 1, is an essential ingredient of the KKLT construction. It allows for control over the higher order corrections in the effective action. So the question, what choice of fluxes lead to W0 much less than 1 is interesting from the point of view of constructing de Sitter vacuum. Recently, these 4 authors have provided a method to carry out such explicit constructions. And this is based on the following observations, that one can get W0 much less than 1 if in the large complex structure limit of the Calabi-Yau, the polynomial part of the superpotential is homogeneous degree 2. So this is a bit technical, let me elaborate. It is known that when one goes to the large complex structure limit, the superpotential is a polynomial which is at most degree 3 and exponentially small corrections. So if this polynomial is homogeneous degree 2, then you get W0 much less than 0. But the same condition of a homogeneous degree 2 superpotential implies that there is a scaling symmetry of W, and that leads to approximately flat direction. Approximate in the sense that it is a flat up to these exponentially small corrections. But we see that here W0 much less than 1 and approximately flat directions are tied. So as before, the condition on the superpotential that it is homogeneous degree 2 here translates to a set of Diophantine equations. Now, if you want to go ahead and carry out Taylor moduli stabilization, examine the phenomenological properties of these vacuums, it is important to understand the full set of solutions to these equations and their properties, as in, do they have any specific properties? So this is what was carried out in this paper in August. And here I will focus on the 2 modulus example, since here the analysis is the simplest. Okay. So in the 2 modulus example, one gets Diophantine equations in 4 variables. They're conveniently paired into M and K to 2 vectors. Now I could write the Diophantine equations, but I think in the view of time, I'll not even write them explicitly. I'll describe the main features of how things go. So in solving these equations, the main challenge is that the flux inner product, which is F(H), is not positive definite. Okay? And this implies that when one writes down the tadpole condition, it does not cut out a compact region in the flux vector space. And that implies that in principle, there are solutions for arbitrarily large values of M and K, and this makes finding solutions quite difficult. But what one can show is that on the solution space, so after you impose the condition that you are on the solution space, this inner product is positive definite in that subspace. And also the ratio of 2 flux quantas minus K1 over K2, recall K1 and K2 were 2 flux quantas, that lies in Farey fractions at 2 times QD3. So recall that Farey n is the set of reduced fractions less than 1 whose denominator is less than n. So with these two conditions, one can effectively look for solutions. It can be helpful to do the last part numerically, which is scanning over the Poisson fractions, but one can enumerate all the solutions. So for example, if you look, I'll just look at one example, which is the 𝗬𝗫 that is obtained from a degree 18 polynomial in CP1169. And this has an orientifolding with QD3134. And we find that there are essentially only two solutions where W0 is less than even 0.1, and I list them. So the point here is, I think that what to show is that you can be very explicit in finding flux vacua and the values that the superpotential takes on. A few comments is that on the other hand, there are statistical expectations for how many vacua there are. And for this 𝗬𝗫, if one compares with the statistical expectation at low W0, as computed by Denef and Douglas, that's of the order of 10 to the power of 6. And this holds in general that these vacua seem to be very low in comparison to the number predicted by Denef and Douglas. So the natural question is, where are they remaining? Are there other families that we should try and find? And when can we trust the statistical approximations? So this is all work in progress. Now, before moving on to the cosmological side of things, I'd like to mention one more topic in type 2b, which is the subject of this paper. So type 2b flux compactifications is the place where we understand moduli stabilization and supersymmetry breaking best. So an important question is, how is the scale of supersymmetry breaking distributed in these? So is high scale supersymmetry favored or low scale or something like that? This question has been studied in the past, but we revisited the question. And what we were careful about is that we did the statistics only over points which correspond to the minima of the modularized potential. So we were actually looking at vacua, so that involved taking this fact into account, that you only do the sampling over the points which correspond to minima. And after that, we found that the results depend on the way moduli are stabilized. For KKLT vacua, we found a power law distribution for the scale of supersymmetry vacua, So N vacuum is the number of vacua in this unit change in the gravitino mass, okay, dN vacua divided by M3 by 2. On the other hand, for the large volume scenario, we found a log distribution. Now, this is contrary to previous results, which put the scale of distribution of supersymmetry to be always power law with a preference for a high scale. So the log distribution is, of course, favors a lower scale, and phenomenological implications of this have been studied in detail by these 4 authors. Okay, so now I'll come to the final topic, which is fast growth of cosmological inhomogeneities, and this will appear this week with 𝗬𝗫 and Francesco Muia. So understanding the inhomogeneities in the observed universe, such as those in the, say, temperature fluctuations in the CMB, is one of the challenges of modern cosmology. And there are 2 aspects to this problem. The first is the generation of the primordial fluctuations, that how did the fluctuations come about in the first place? And so this, something like inflation can give you. And the second, equally important, is the evolution of these perturbations through the history of the universe. And the work I will describe is about the latter. So let me quickly recap some basics about the evolution of cosmological perturbations. The key players are, of course, the tendency of gravity to collapse, pressure and expansion of the universe. They counteract this. Now, in flat space, there's the Jeans instability, which says that for long enough wavelengths, an overdense region is going to collapse in exponentially fast time in the linear theory. But things are a lot slower in an expanding universe. For instance, in a matter-dominated epoch for sub-horizon modes, the growth is proportional to the scale factor, which is power law in time. In a radiation-dominated epoch where there is pressure, it's even slower. It goes as log of the scale factor. In the standard lambda CDM model, inhomogeneities grow and structures form in the matter-dominated epoch. But as we probe the inhomogeneities in the universe at various length scales and greater accuracy, growth of perturbations, and particularly if we have scenarios of fast growth, they can be very interesting. Now, let me come to our results. So I'll first describe the setting, the main ingredients, and the results. So our setting is an early matter-dominated epoch in the universe. So this is before Big Bang nucleosynthesis. There is the matter-dominated epoch. And this is a generic feature in string cosmology. And then a scalar-mediated force between the constituents in those epochs. So you have a scalar field that's mediating the force. And that, again, occurs commonly. The coupling is via the stress of the trace tensor. So given these two, we find that inhomogeneities can go very fast. That is, delta t grows with an exponent of the scale factor that can be much, much greater than 1. So let me come to the system of equations. There are 3 components in the universe that will play a role. One, so there are 2 cosmological fluids, which will be described by B and psi, and we will be using their stress tensors to describe them. And there's a scalar field. So these are the 3 components. And the stress tensors of the individual fluids are not conserved. There are violation terms. These violation terms are proportional to the traces, their traces, and the gradient of the scalar. And this system has been well studied in the past. It starts from work by Damour, Gibbons, and Goodlack. Amendola has explored various aspects of this system. And 2 is just for the purposes of illustration. You could have multiple components here. So because of this violation terms, the various components will in general exchange energy. Betas are the couplings. An order 1 beta is a Planck surplus coupling, but you can get larger values of beta in supergravity. So now let's come to our solution. Firstly, we find a new homogeneous background of this system of equation. So let me first describe features of this background. It has the following properties. Firstly, in asymptotic time, the energy exchange between the components stops. Okay? And the energy density of all the components, they fall off as matter. So everything is diluting as 1 over a cube. And that's good because that's where one can expect fast growth. And the scalar field is just oscillating about its minimum, the Hubble having fallen below its mass. And this, we end up in the solution for a large class of initial conditions, although we haven't charted this out fully, but this seems to be quite generic. It's like a tracker solution. So just I'll show a slide with the evolution. You have omegas, which are the fractional energy densities. and they are evolving. N is the number of e-foldings of the universe, and you see that within 2 e-foldings, everything settles in. The fractional energy densities don't change. Okay, now let me come to the perturbations. Having described the background, let's study perturbations in them. And for simplicity here, I will just set one of the couplings to 0. And we'll focus on modes that enter the horizon well before the scalar begins to oscillate. So this is a coupled system. You are looking at perturbations of there's Einstein gravity. There are the various components. But for the psi field, the equation is well described by this equation. And let's look at that. So this is the equation that describes the perturbations of psi, delta psi being the fractional overdensity. Primes here are derivatives with respect to the log of the scale factor. And so that's the number of e-foldings. Omega psi is the asymptotic value of the fraction of energy density in the psi fluid. And you see that suppose I set omega psi equals to 1 and beta equals to 0. So that's the standard matter dominated epoch. There is the solution delta going as e to the power of n, which is just the scale factor. So we recover the usual story of linear growth for beta equals to 0. But with non-zero growth, one can get much higher exponents. And the growth is essentially controlled by the square root of omega psi times beta squared. Omega psi, of course, depends on beta. And but for instance, if I set beta like equal to 15, one gets a growth factor of 5.5 growth exponent. And this is very fast in the sense that if you start with primordial fluctuations, which are of the order of 10 to the power of -5, the kind that people talk about in the context of a scale invariant perturbation coming from inflation, then within 1 or 2 e-foldings, the perturbations go nonlinear. Now, this matter-dominated era must end before BBN so as to accommodate the successes of nucleosynthesis. But a fast growth in this pre-BBN era can have many interesting implications, and we've just started to explore these. The first is compact objects. We can expect to form compact objects or primordial black holes. And our parameter range allows for primordial black holes in the lunar mass range, which is very interesting from the point of view of dark matter. The second is gravitational waves. When you have fast growth of perturbations in the universe, you produce gravitational waves. And these are in the high frequency range. So high frequency gravitational waves are expected to be a new probe of early universe. So in principle, one can have signals for these probes. So other than that, there should be many interesting implications for things happening at the shorter length scales. So that brings me to my conclusions. I talked about 2 things. The first is string compactifications, where I described novel solutions with n equals to 2 supersymmetry. I looked at how one could get solutions with W0 much less than 1. We also have some systematic methods to look at these, and there is some interesting structures in the Diophantine equations that we are getting. We hope to pursue this further. We have been using very elementary methods till now. On the phenomenological side, I looked at supersymmetry breaking. There we found a new distribution, a log distribution. And finally, I looked at cosmologies, where one can have a very fast growth of perturbation, cosmological perturbations, which should have some interesting implications. And to summarize, I'll say that there's many things to explore on both the sides. So thank you.
Okay, thank you very much for the excellent talk. So we have some questions. So first, we can let Alok Mishra ask his question.
Okay, hi Anshuman. I just had a couple of, sorry, yeah. So first off, Shiroman, do I have the permission to ask 2 questions, or I ask one, I wait my turn again?
You can, whatever.
Oh, okay,
you wish,
I'll be real quick. So I've got 2 quick questions. So just correct me if I'm wrong. Since you guys have not, at least in what you talked about today, you have not explicitly included high derivative corrections. So let's say the alpha prime cube corrections. So you are within the regime of no scale supergravity, right? Is that right?
Yes, for the first part, I had not. When I was looking at those, when I was just focusing on the complex structure and dilaton.
Yeah. So actually, that brings me to my first question, which is the following. So we know that there's this, I think, which is something which you probably alluded to, or I'm not sure, this beautiful conjecture by Douglas and Ashok about essentially looking at the no-scale vacua. So looking at the total number of no-scale flux vacua.
Yeah.
And there we know that it's basically given in terms of an integral over the moduli space. Back when this thing came out, I, one of my, in fact, back then, an undergraduate first-year student, as a summer project, we actually explored one of these 2-parameter Calabi-Yaos of the projective variety that was actually 11226. And so this, I think you made some statements about not really getting a power law in terms of the number of vacua. What we found was the following, that if one was working near or away from the conical loci, let's say probably there was just one of the projective variety of the Calabi-Yau that we looked at. So if one was away, one was actually getting a power law, and the logarithmic, I think you talked about some logarithmic dependence. So that is something which was actually when you were working near the conical locus. And in fact, that was interpreted as an attractor solution. So, I mean, that's sort of a remark / question to you.
Yeah, so I think that the distributions that I was looking at was the scale of supersymmetry breaking. So this is, I think this is the distinction that we made, that we computed the distributions after doing the moduli stabilization. So this, I mean, so for this part of the talk, we were actually incorporating the Kähler moduli stabilization. And so it could, so that's the reason for the difference with the old result of a power law distribution for the scale of supersymmetry making. What could be true is that the log distribution that you found could actually map to the logs that we have found after moduli stabilization, as in that part of the moduli space might be dominating for the LVS solution. That's what we have not looked at. But I mean, the reason why I think people found power laws for the scale of supersymmetry breaking is that they had not incorporated moduli stabilization. In fact, the reason why our results for KKLT and LVS are different is that we are incorporating the Kähler moduli stabilization in this part, in that later part of the talk.
Oh, so that means I probably misunderstood. I mean, I thought at some point you were talking about just the number of flux vacua not being a power law.
No, this is after incorporating the scale. This is after including supersymmetry breaking. So this is once you have stabilized the moduli, you ask that how does the number of vacua change as I change M3/2? And in one case, that goes as 1 over M3/2, and in the other case, that is proportional to M3/2. So okay. It's a slightly different question.
I see.
But I mean, the logs and the power laws do show up. And it could be related to your initial understanding of the distributions that you're talking about. But this is, these distributions are about the scale of supersymmetry breaking. So this is dn vac divided by dm3/2. So how they change the number of vacua in an interval of m3/2.
Yeah, I mean, I just feel that intuitively, probably you would need to actually explore two regions, the complex structure moduli space, one near, one away from the conical singularities.
Yeah.
Especially if you're looking at the projective varieties, maybe. Okay. So
yeah. I think maybe that's related, but the way we kind of do this computation is that we boil the problem down to just looking at the distributions of W0 and G string. So that in principle takes into account the distributions that you are talking about.
Okay, and a thorny question, but I hate to put you on the spot, but still, I mean, so how does, how does this, I haven't followed the story for a while, but how does the small W0 vacua address the swampland conjectures?
Well, see, I can tell you my view of this whole story in the sense that there are various things that need to be done very explicitly for us to be more and more confident about the existence of a de Sitter vacuum in string theory. And one of the things that I mentioned is that the KKLT construction requires is a very small value of W0. Now, that is not easy to achieve because you essentially have to, you're dealing all the flux quanta are integers. Now, by tuning these integers, you want a small number. With statistical expectations, as I pointed out, the statistical expectations were that they're there. Now, you might like to go a step further where you actually find them, okay? And these recent developments show that you can find small W0 where you specify the Calabi-Yau, you specify all the flux quanta, and you compute W0 and you get a small number. So that's making one part of the set of things that we need to do in a more solid footing. The other thing about small W0 is that small W0 is very essential to control the higher order corrections in the effective action. So even if you believe, say, the swampland conjectures and you want to construct string vacua in the region where you trust them, having explicit constructions of small W0 is equally useful. I mean, the same challenges of moduli stabilization and understanding the system also come up if you want to construct a model of quintessence. So overall, this adds to the kind of things that we need to be very explicit about. And this is one aspect which I think has been cleaned up. There are more questions, but this helps.
I think Yusuf Bena would be very, very annoyed with any success that would be.
No, well, I think that, look, I mean, it's not that there are other questions left. So there's no reason to be, I think there's no reason to be annoyed by a table where they're just numbers. I think he won't, I mean, you know, there are things that we just have to clean up. And see, the other thing is that once you do these things, apart from knowing whether you can have de Sitter vacua or you're realizing quintessence, you will learn things about the phenomenology. As in, when you want to, say, compute the distribution of various quantities, what are the properties of various vacua, you need these kind of computations. So, yes, these are all useful, and as I said earlier, I mean, they will also be useful in getting information about string compactifications in general. It is enlarging our understanding of string theory in some sense.
Okay, so I think ICTS had a question. So.
Hello. Anshuman, this is Loganayagam here.
Yes.
Yeah, so I just wanted to ask you a question about this cosmological scenario that you presented at the end. This fast growth of cosmological inhomogeneity, like why doesn't this, wouldn't it completely destroy the fact that the CMB anisotropies are suppressed and so on? Like, why wouldn't this contribute to?
Yes, so the thing is that these are modes that that enter the horizon well before the CMB scales. So this is at a short scale. So this will not affect things that are happening at the CMB scales. So this is a completely different length scale. So if you believe in something like inflation, what would happen is that you start off with everything which is scale invariant, as in you have delta equals of the order of 10 to the power minus 5 for all scales early on. And then you evolve. So some scales will grow faster than the others. So this is a computation of what's called the transfer function in cosmology. So that's it.
Okay, just one more question. So you were talking about these gravitational waves and so on at some point in your talk. So you have some estimate of like what kind of, let's say, B mode polarizations will show up and so on. Is that how?
So this is not within the context of the CMB. This is just a stochastic pure gravitational wave. So you should think of it as trying to detect the gravitational wave directly. So this is in the higher frequency range. We go around 10 to the power of 2 hertz with LIGO. So this can be we've just done the ballpark estimates. This is probably 4 or 5 orders of magnitude more. So here there are no experiments, but there is an active community which wants to have experiments in this. So they want to join the gravitational wave collaboration team. But this, because the earlier you have the phenomena, typically you get higher and higher frequencies. So this can be a new probe for early universe.
So sorry, just to make sure that I understand. So you're saying this only affects the larger part of the spectrum, and it does not have any effect on this R and so on, the tensor to scalar ratio.
Yeah, it will not. It's a different. It's in a different range. Its origin is different from inflation. Okay, and this will be just like a stochastic gravitational wave, which will not have any direct effect on the CMB scales.
Okay, thank you.
Okay, so let's thank Anshuman for a very nice talk. And okay, we're going to move on to the next speakers. So the next set of speakers are 4 speakers who each have 15 minutes each. So we'll be very strict on time. So you will have exactly 15 minutes. And the first speaker is Suchetan Das from IIT Kanpur, who will talk about chaos under periodic drive. So please begin now.
Yeah, thanks, Roman. Am I audible?
Yes.
Yeah. Okay. Can you see my slides? Yeah. Okay.
Yes.
Okay. Thanks. So this talk is basically based on our current work with 𝗬𝗶𝗶 session, Arnab P, 𝗦𝗵𝗶𝗿, 𝗬𝗫 and some broad motivation for our work. So we know what is OTOC. So OTOC, or out of time order correlator, is basically a useful probe for quantum chaos. So it tells that the operator growth, or sorry, so the commutator growth of 2 operators of W and V in some state, if it has an exponential growth, then it can be probed through OTOC, or the out of time order correlator, or the decay of the OTOC, which is in this form. So the exponential growth in this way is characterized by the decay of OTOC, where this lambda is the Lyapunov exponent, and this v is the butterfly velocity, and t star is the scrambling time. So generically, this chaos is basically the both properties of theory and state, because the theorem is it is the property of the chaotic Hamiltonian also, and state means it is the property of also the state. Like for example, like large C 2D CFT in thermal state is chaotic, but if you consider the like minimal model in 2D CFT, and in thermal state it is not chaotic. Okay. So now one could ask another question is like that which safety has holographic semi-classical Berg gravity description. So we already know that large C large gap safety 2 has this description, and recently after MSS bound, that maximally chaotic theories which saturate this bound, that's MSS bound, it has also the description of holographic semi-classical gravity. So now from these two facts, one can ask that do large C safety 2 is always chaotic or maximally chaotic? The answer is actually depends. It is also, of course, chaotic in thermal state or in equilibrium, but it is not chaotic in vacuum. Like it has power law growth in OTOC in vacuum state. So this statement that maximally chaotic theory has holographic Berg dual, it is only in equilibriums, only in thermal equilibrium case. Now, so the question is that what about the chaos or the chaotic property in out of equilibrium scenario? Like one can ask, like, is large C safety 2 is chaotic beyond thermal state, or can we have any notion of scrambling in an open system, or any bound of chaos in non-equilibrium system? And or what is the role of scrambling in a non-equilibrium system to reach equilibrium? Like what is the role of scrambling to reach in thermalization process? So all this question actually has some non-equilibrium setup, and and also this question may set important insights in black hole phase, like the formation or evaporation process of black holes. And also this question may put in important criteria on non-equilibrium system to have gravity dual. Now, to study these questions or this out of equilibrium question, we must go beyond the thermal state or time independent Hamiltonian dynamics in to compute OTOC. Right. So if we consider any out of equilibrium scenario, we must go beyond thermal state, and of course we can go beyond the static Hamiltonian dynamics in note if compared to OTOC. So one question is like, what is the scrambling notion of scrambling in quantum quench process, and or in particular in 2D large C CFT, if can we consider any can we have any example of 2D large C CFT is chaotic in any other non-trivial non-equilibrium state, like particle arbitrary state in the context of quench, which actually mimic thermal state at last time. So for this type of question, you see the Arnab P talk today and afternoon. Now another question is that is the 2D large C CFT is chaotic in vacuum state due to any non-trivial Hamiltonian dynamics, like we calculate OTOC in vacuum state, but due to the non-trivial Hamiltonian dynamics, is there any notion of chaos in large C 2D CFT? The answer is yes, and that is the part of my talk, and the answer is that for driven CFT which has no equilibrium analog. Okay, so let's go with the plan of my talk. So in this talk I will discuss some key result of an ongoing work of computing OTOC in driven 2D CFT. So plan of the talk is the following: that we first give a brief review of periodically driven CFT, like the emergence of different phases, like heating phase, non-heating phase, etc., and the observables like entanglement entropy, total energy, and classical Lyapunov in different phases. Then we'll go to our setup of OTOC under periodic drive, and we'll see some unusual feature of cross ratio. Then we'll see the exponential growth in heating phase, and we also demarcate different phases like heating and non-heating phase using this OTOC. Also, since this drive actually imposes a special inhomogeneity in the driven Hamiltonian, so this implies the butterfly velocity and scrambling time is also position dependent. So our slogan is that 2D CFT actually drive how it drive OTOC scale. Okay. So first we'll briefly review the periodical driven CFT. So we just start with some state or ground state or psi naught or some state, and we just drive it through the Hamiltonian H0 and H1. Suppose for this case, suppose for the simplest case, So here H1 we drive with the Hamiltonian H0 for the time interval tau naught, and we drive H1 for the time interval tau 1, and we follow this periodically up to n times. So it is an n driven system. So it can be written in this way, and it also generalized to arbitrary SL2, arbitrary U. I mean H1, H0, H2, H3, and etc. etc. And here this n actually plays the role of the stroboscopic time, which is basically the time is here n into tau naught plus tau 1 for these cases. So now here the H0 is basically the safety Hamiltonian. This is and H1 is the driven Hamiltonian or the deformed Hamiltonian, and here is this factor is the special inhomogeneous factor, and it has also imposed a periodic boundary condition at 0 and L, and the important point is that this Hamiltonian can be written in terms of L0, L1, and L-1. I mean all the SL2 generators in terms of SL2 generator. So in this case, this H0 and H1 actually define this SL2 drive. And this, in the Heisenberg picture, where you can consider the operator evolution of this driven system. So this in the Heisenberg picture, this operator evolution can be mapped as recast as an coordinate transformation from Z to Zn, where Zn is the Mobius transformation or some in this way. So this picture actually tells that this simple setup tells that Mobius transformation actually dictates the operator evolution of driven CFT. So all these discrete type can be generalized to continuum case, where the HT is the continuum Hamiltonian, the driven Hamiltonian. When F1 is 0 and Ft is 1, then it is the H0. But when F1 is 1 and we consider the Ft is this way, where F0 is the driving amplitude, and omega d is the driven frequency, drive frequency. And for this continuum case, one can also consider this this U. One can also construct this U, and in this following way, and similarly, like the discrete drive, one can also construct this n-driven U in terms of this transform matrix, which is the Mobius transformation. So we just let us briefly review the basic the result already know in the literature. So in the n-cycle drive, this Mn is a transform matrix, and so it contains 3 types of Mobius transformation, and it can be characterized these 3 Mobius transformation in terms of the trace of the transform matrix. And if it is greater than 2, this is called hyperbolic, and it is less than 2, then it's elliptic, and it is equal to 2, then it's called parabolic. And these 3 transformations actually characterize the different phases, like heating phase, non-heating phase, and phase transition line. So for example, for total energy, if we compute total energy in the driven system, then it has an exponential growth in n for heating phase, and it has a power law growth in phase transition and oscillator in non-heating phase. Similarly, similar structure exists for entanglement entropy, which has linear growth in n in heating phase and logarithmic growth in phase transition. And one can also define a classical Lie pronoun, who actually tells the growth rate of this matrix Mn, this transform matrix Mn in n. So, and it is always greater than 0 for heating phase, and it is 0 for both non-heating and phase transition. So similar analysis can also hold for continuous drive case, where when an useful parameter is alpha, and alpha is this way, which is a function of both drive amplitude and drive frequency, and et. And when alpha square is greater than 1, then it is called heating phase. Alpha square less than 1, it is non-heating phase, and alpha square equal to 1 is the phase transition. So now we'll come to our work. What is that so far we have only seen that the lower point function has been studied in driven safety, but here we'll consider the higher point function, 4-point function, 4-point OTOC in largely 2D safety. So this is the setup here, the W, but W is at n and special at 0, and P has 0 and special position is x, and n plays the role of stroboscopic time. So the general strategy is to compute the Euclidean correlator, and then we have to analytically continue to real time. That is, here the stroboscopic time is nt. So nt goes to nt plus I epsilon I is the analytic continuation, and from this defined epsilon ordering actually dictates the defined time ordering, that is time order and after time order correlators. So main object of analysis in this case is the cross ratio eta. So it has been shown that when eta greater than 1 for eta is greater than 1 for OTOC and eta less than 1 for TOC, at least for safety case. Now, now in our driven safety setup, we have seen some unusual spatial structure in eta. So for example, for eta, when eta we have a certain point of x for which eta equal to 0, we'll call this a fixed point. So it is a fixed point of this drive for when eta equal to 0. And also we have found an range, this range for which eta is always less than 1. So in heating phase. So this means that in this case, we have same TOC and OTOC. So this means that the X has the range of 0 to L, but this portion of this range, it has always less than 1, but this portion of this range, by 0 to this, and this is the fixed point. So 0 to fixed point, we have eta is greater than 1 for OTOC and eta is less than 1 for TOC. So the key result of our is that, that for Larcy 2D safety, we get that we know that for Larcy 2D safety, eta greater than 1 is implies that we have an exponential growth in OTOC, and eta less than 1 gives the trivial time order correlator. So in our cases, we see that in heating phase we have the exponential growth, the chaotic growth of OTOC, and in non-heating phase we have that this OTOC is oscillatory, and in the phase tensor line it is the power law growth of in time in n. But the theta and s is the parameter in the drive, and it is only true for this range of x. So these are also demonstrates that OTOC actually demonstrates different phase structures like this heating, non-heating, and phase transition. And also Lyapunov in this heating phase exactly matches with the classical Lyapunov we actually defined earlier. But the question, the classical notion does not distinguish chaotic and integrable theory like Larcy CFT and minimal model. It does not. It is always chaotic in heating phase. It is always chaotic in classical notion. But in the quantum, from the OTOC perspective, we see that it is it has different behavior for minimal model and Larcy CFT. So also we see that the important result is we see this chaos is only in vacuum state and it has no equilibrium analog. And another feature is the scrambling time is position dependent, and it is the feature of spatial inhomogeneity in the drive. And another result is the butterfly velocity, and here butterfly velocity is also position dependent. So this is the form of the butterfly velocity, and we see that the hello.
Time is almost up, so just yeah.
Oh, I have just one more slide. Just stop there. So it has this structure like it has both superluminal and subluminal velocity regime, and it has okay. And also we have other result like since the spatial inhomogeneity actually breaks the translational invariance, so we can study also study this type of correlator which has different from which we get different result. Like we get the similar Lyapunov growth for different phases, but we have different fixed point for eta and different range of x for which eta greater than 1 in the OTOC. And we have also more integer structure for butterfly velocity and etc. etc. So and we also generalize this for periodic drives, but the generalization we get is still same. And there is some future direction like what is the bulk story and what is the connection to horizon formation and what is the operator growth in this language, and is there any new holographic criteria for outcome equivalence system from this, etc. etc. Thank you.
Okay, so thanks. So actually we really have time for questions, but if anyone has a quick question, you can ask.
I ask one.
Yes.
Okay,
yes.
very quickly. Yeah.
So for this 4-point function, you said that this was the 4-point function of a holographic CFT. So presumably you were using some block.
Yes, yes. There's a Larcy CFT. There's 𝗵𝗶𝗶 block. I mean identity block.
Yes. Yeah. So what kind of block? Like, is it the heavy light block or?
Yes, heavy light block.
So if you used like some the block of 4 light operators, do you still expect that this oscillatory or this exponential growth to still remain, or is it only for the heavy light block that you see?
Yeah, this is only for the heavy light since we have an analytic expression, but for 4 lights.
Even for 4 lights, you also have an analytic expression. So. Do you know what happens in that case?
No, that I don't know actually, but yeah, that's a good question. But yeah, But it is purely for the like the Stanford case that heavy ladder block. We only consider this. Yeah.
Okay. Thanks.
Okay, so now we'll move on to the next speaker, who is Arnab Saha from HRI, and he'll speak about one loop amplitude from generalized scattering equations. And please stop within 13 minutes if you want to answer questions.
Yeah, am I audible? Is my screen visible?
Yes.
Okay. First of all, I'd like to thank the organizers for giving me the opportunity to present our work here. So this talk is based on these two papers written with Abhishek 𝗬𝗪𝗍 and 𝗦𝗵𝗶𝗿. So let me begin by giving an overview of our work. CHY or Hlacher-Hay-1 formalism is a remarkable development in S-matrix program. And using this formalism, several quantum field theory amplitudes can be computed using integral representations over moduli space of punctured Riemann spheres or CP1. And there are various aspects why CHY is important. One of them being it replaces the conventional technique of finding scattering amplitudes using Feynman diagrammatics, and several important properties of S-matrix such as color dynamic duality, double copy relations, and factorization properties under soft limits and collision limits can be studied very efficiently using the CHY formalism. And scattering equations play a very important role in this formalism. Scattering equations basically map the singularities of the kinematic space to the singularities of the moduli space of punctured Riemann spheres or CP1. And recently, CHY, 𝗪𝗪𝗍𝗪 and 𝗦𝗫𝗪, they introduced generalizations of the scattering equations, which are now defined on higher dimensional projective spaces CPk-1. An important motivation behind such generalization comes from the fact that standard scattering equations defined on the space of n points on CP1 can also be thought of as scattering equations for n points on CPn-3. A well-studied example with this generalization is the bi-adjoint scalar amplitudes, and in this work we'll focus on these amplitudes. These amplitudes have realizations in terms of what is called Grassmannian cluster algebras. And in this work, we use GR36 cluster algebra. We relate the singularities of k equal to 3, n equal to 6 amplitude to 4.1 loop integrand in the bi-adjoint cubic scalar theory through the D4 cluster polynomial. And we also study various factorization properties and soft limits of these amplitudes. So this is the outline of my talk. First, I'll introduce CEGM formalism, then briefly mention about cluster algebra, and then I'll talk about our work, one loop amplitude, and finally end with some conclusion. So these are the scattering equations, so which play important role in CHY. There are n such scattering equations corresponding to the total number of external states in the scattering process. And SAB, these are the Mandelstam variables, and here we are dealing with massless particles. So these are just dot products of two null momenta, Ka and Kb, the external states. And sigmas are the punctures on the Riemann spheres. And one can check that these scattering equations are invariant under SL2C transformations. Therefore, one can actually fix the positions of three punctures. And therefore, not all of the scattering equations are important. We get a set of n-3 independent scattering equations out of n such equations. And using these scattering equations, one can write scattering amplitude by this integral representation, where the scattering equations come in the arguments of the delta functions. And because of the presence of these delta functions, this integration is actually localized on the solutions of the scattering equation. And In, this is the integrand which contains information about the specific theory for which we want to find scattering amplitude. And in general, In depends on external data like momenta, polarizations, and also the punctures. An example of CHY amplitude is here we take bi-adjoint cubic interacting scalars, where the scalars live in the adjoint representations of two unitary groups. And the integrand for this amplitude is given by these two copies of particular factors, where the particular factor with a particular color ordering is given by this expression, where in the denominator we have the products of differences of the punctures. And so this In, it stands for the color stripped part of the amplitude. We also have the trace factor which is taken out. Now, this scattering equations can be obtained from this quantity, which is called generalized potential function, which is defined in this way, where this AB round bracket stands for the determinant of 2 by 2 minors, where the sigmas are the homogeneous coordinates on CP1, And then we can go to the inhomogeneous coordinates by this expression by dividing one coordinate by the other, and we get this quantity. And so this will serve as the determinant here. And when we extremize this generalized potential function with respect to these inhomogeneous coordinates, we obtain the scattering equations. Now, this can be generalized to higher dimensional projective spaces from CP1 to CPk-1. And here we take the determinant of k cross k minus and x1 to xk-1. These are the inhomogeneous coordinates on CPk-1. And using this, we can generalize the potential function in this way, where SA1, A2 to AK. So these are now called generalized Mandelstam variables. And we can impose conditions like momentum conservation and massless conditions in this way. So when we, for every A1, when we sum over the other indices, we get the momentum conservation. And by demanding that whenever two indices repeat, those quantities are set to 0, we get the massless conditions. Now, a priori, these generalized Mandelstam variables do not have much physical interpretations, although in our work, we have given a physical interpretation for the particular case of k equal to 3 and n equal to 6. And like before, the case of k equal to 2, we obtain the generalized scattering equations by extremizing this generalized potential function with respect to the inhomogeneous coordinates. So all total, there will be k-1 times n number of equations. But again, these scattering equations are invariant under SL-KC transformations. Therefore, one can actually fix the positions of k plus 1 of the punctures. Therefore, to obtain the set of independent scattering equations, we have to remove those many number of equations. So as an example, for k equal to 3, we have these two sets of scattering equations. And now we denote the moduli space on which the scattering equations are defined as xkn. And this is actually given by Grassmannian k, n modulo c star raised to the power n minus 1. Grassmannian grkn is the space of all k planes in n dimensions. So therefore, to begin with, we have k into n number of coordinates. And because of the GLK symmetry for the k planes, we can take out k square degrees of freedom. And on the top of that, we have scaling degrees of freedom available, which is given by this torus action. So we remove further n minus 1 degrees of freedom. And therefore, the dimension of this moduli space reduces to this quantity, k minus 1 times n minus k minus 1. And we can analogously define the particular factor, generalization of the particular factors in this way, where in the denominator, we have the product of the determinants of k by k minus. And by taking two copies of the particular factors with particular color orderings alpha and beta and integrating over the moduli space of punctured CPk-1, we can then define what is called bi-adjoint amplitudes or generalized bi-adjoint amplitudes. And it is these amplitudes that we'll be interested in this work. So I'll mention briefly about cluster algebra here because this will be important for our study. Clusters can be defined as quiver diagrams, which are oriented graphs equipped with arrows connecting different nodes, and each node is assigned a cluster coordinate. GR2n cluster algebra can be represented by triangulation of an n-gon, and in this picture we have GR25. So we have triangulated a pentagon, and corresponding to this triangulation, we can find this cluster quiver. And here, there are like 2 unfrozen nodes, and rest are the 5 frozen nodes. So these nodes are Fluker coordinates. Fluker coordinates are the same as the determinants that we saw earlier, and these are also known as A coordinates. And I should mention here that GR2n cluster algebra is related to n.3 level phi cube amplitude. And in our study, we will go beyond GR2n and study GRKN in general because they are related to the CGM amplitudes. So in GRKN algebra, every cluster has k-1 times n minus k-1 number of mutable nodes. And we can have some geometric objects corresponding to these cluster algebras, which are called cluster polytopes. And the dimension of this cluster polytope is the same as this k-1 times n minus k-1. These cluster polytopes have the property that they have boundaries of codimension 1, which are called facets. And we have ray vectors which are normal to these facets. And every vertex of the cluster polytope can be mapped one-to-one with Feynman diagram. So here, for example, we have the GR25 cluster algebra, which is also known as A2 cluster algebra. And correspondingly, we have associahedron drawn here, and every vertex of the associahedron corresponds to the tree-level Feynman diagrams, which come in the planar order 5.5 cube amplitude. So we have to find the compatible set of ray vectors to find these Feynman diagrams. Okay, so now I'll come to our one loop amplitude. So we are interested in GR36 because we study k equal to 3 and n equal to 6 amplitudes here. So for GR36, there are total 6 frozen and 14 unfrozen coordinates. And sorry. Okay. Yeah, I'll try to wrap up soon. So in GR36, there are total 6 frozen and 14 unfrozen coordinates. However, GR36 tropical fan has 16 ray vectors, and the mismatch can be remedied by introducing 2 quadratic coordinates q1 and q2 like this, and using these 2 quadratic coordinates we can modify our generalized potential function in this way, where we introduce SQ1 and SQ2 to be 2 new Mandelstam variables, and using this potential function we can find we can find our amplitudes by the usual way, the scattering equations. And yeah, so what we have done here is that this GR36 Spire-Williams fan that we saw earlier is related to D4 cluster algebra. And in this paper, 𝗏𝗏𝗃𝗃, Salvatore and Thomas, they have shown that a Dn cluster polytope is an n-dimensional polytope with n² facets, and it is related to n.5 cube amplitude at 1 loop. So we use D4 cluster polytope to relate to 4.1 loop integrand in 5 cube theory. And the cluster string integrals provide stringy canonical forms for the generalized associahedra of a finite type cluster algebra. And taking the quantum field theory limit, that is alpha prime going to 0 limit of D4 cluster polytope, we obtain 4.5 cube integrand at 1 loop. And in this work, we have mapped the singularities of D4 polytope to the generalized Mandelstam variables of the modified 3/6 CEGM amplitude and interpret the latter as 1 loop integrand of 5 cube theory. I'll just shortly mention the construction that so D4 polytope which has 16 facets, they can be labeled by these variables. And in this paper, these authors, 𝗏𝗏𝗃𝗃, Salvatore and Thomas, they have used these labels to draw Feynman diagrams. So there will be total 50 such Feynman diagrams corresponding to the all possible 4.1 loop integrand. So we have the Feynman diagrams, and in our work, what we have done, we have used the worldsheet coordinates that we obtained from the cluster string integrals and find a map between the cluster variables and these generalized Mandelstam variables that we had earlier. So in a way, we have now given a physical interpretation of these generalized Mandelstam variables. And so what finally we can do is use these generalized Mandelstam variables to draw Feynman diagrams. So now we have the interpretation of these generalized Mandelstam variables as singularities of 4.1 loop integrand of 5 cube theory. So we have also studied some factorization properties like taking the forward limit when you restrict to some boundaries of the polytope, we get the forward limits, and similarly one can also study soft factorizations. And in our work, we have specifically studied a double soft limit. So in our earlier work, we had the double soft factor for general k amplitude, which is given as product of 2 soft factors sk-1 and sk, and the scaling goes as 1 by tau to the power 3 k-1 for this double soft factor, but tau is the scaling parameter by which the external states are taken soft. And here specifically we have taken n-1 and nth legs to be soft. And in this particular work, what we have seen is that this double soft factor actually corresponds to one particular facet of the D4 polytope. And this particular facet.
So I'm going to have to stop for questions because it's 15 minutes, or you can finish and no questions.
Yeah, I can finish. I mean, I can finish in 1 minute. If you give me
and no questions.
Yeah. I mean, whatever. So I can just stop at this. Like I'll just say one word. So this double soft factor when restricted to this particular facet, that actually corresponds to A3 sub-algebra, A3 cluster algebra. So yeah, okay, I'll stop with this.
So Kaushik had a question.
I have a very quick question.
Yeah.
Yes.
Going back to your diagram that you drew, the pentagon associating the vertices to the Feynman diagrams.
Yes.
Is that the associahedron or not? Because in the associahedron, it's not the vertices, but the sides which will be associated to this Feynman diagram.
So, I mean, yeah, what we are talking about, it is a dual of that picture.
The points where some of them come together, some of the points. So these are the singular situations.
Yeah, so I think, I mean, this is also what is called associahedron, but what the picture that you are saying, that is a dual of this. So here the ray vectors are actually normal to these facets.
Okay.
Does that answer your question?
Even in the dual, I think that statement is correct. I mean, the vertices are actually they correspond to particles coming together.
I mean, so the okay, so the
edges that will correspond to the Feynman diagrams.
No. So in this picture, the edges correspond to these Mandelstam variables. So and at the vertices, we have like two corresponding Mandelstam variables coming together, and they form the two propagators of the Feynman diagram.
Yeah, they will come together. That's the point. Yeah. Okay.
Yeah. So the vertices will actually represent the Feynman diagram.
Another quick comment is, do you know how? So in this connection to the DN-Quiver's, doesn't work beyond the cubic theory. It only works for 5-cube theory. That I think one can. I mean, it's easy to see. So do you have any idea how to generalize it to any other polynomial?
Meaning how to obtain for 5P kind of theory.
Yeah, I mean beyond 5-3, this connection to the DN-Quiver's will not work.
I see. Yeah, that okay. I mean, I don't have much to say about that. Yeah, I think there are both polytopes and those constructions.
Okay.
In the discussion. So next speaker is Renjan John from IIT Pune, and he'll speak about anyonic correlation functions in Chern-Simons series. So 13 minutes plus 2 minutes for questions.
Okay, thanks. Can you see the screen?
Yes.
Okay, so the title of my talk is Anyonic Correlation Functions in Chern-Simons matter theories. This is based on a work done with Yatharth Gandhi, who was then a BSMS student, and Sachin Jain from IIT Pune. So in a three-dimensional CFT, it has been shown that a generic 3-point spinning correlator has 3 structures, 2 of which are parity even and 1 parity odd. For example, in the case of the 3-point function of stress tensor, one gets a parity even contribution from free boson, another parity even from free fermion, and a parity odd contribution which doesn't come from any free theory. So while the parity odd structure contains the Levi-Civita tensor, and there is no apparent relation between the 3 structures that contribute to the correlation function. In this talk, what we would show is that the entire 3-point CFT correlator can be obtained from just the free bosonic or the free fermionic theory. We will then apply this in the context of Chern-Simons matter theories, and there we'll see that the full 3-point function can be obtained from the same correlator in the free theory after an appropriate multiplication by an anyonic phase factor that depends on the coupling. Before we go into the details, we'll first discuss the important ingredients that go into our analysis. So we begin with a discussion on 2-point functions, which should hopefully set the stage for 3-point functions. Let us begin by considering the 2-point function of the conserved spin 1 current, denoted J. The even part of the correlator is given by a project, the transverse projector times the momentum, magnitude of the momentum, and the odd part of the correlator is given by the epsilon Levi-Civita tensor contacted with the momentum. Now, given these expressions, one can easily check that the following relation holds between the odd and the even parts of the JJ 2-point function. Similar relations hold for TT 2-point functions also. And if your theory has higher spin currents, then such a relation between the odd and even parts continue to hold even for the 2-point function of higher spin currents. In our analysis, we make use of spinor helicity variables, in terms of which the relation between the even and odd contributions to a correlator becomes manifest. So let us have a very quick review of these variables. We write momenta in terms of SL2C spin as lambda and lambda bar, and they're related to the momentum through such a relation. And here epsilon is an antisymmetric 2x2 matrix, which defines the spinor brackets, which are the dot inner products between your spinors. Now a spinning operator has two helicities, which we denote by plus and minus. And when the tensor indices of the operator in momentum space are contacted with polarization vectors, the operator gets projected along one of the two helicities, and we denote them by J plus or J minus. Now in spinor helicity variables, the 2-point function has a unique structure, and the even and odd correlators differ only by a factor of I. For example, for the spin 1 current, the even and the odd parts of the 2-point function are given by this bracket here. And notice this factor of I here. So the entire 2-point function, which is like a C1 even plus C2 odd, is given by such an expression. Now, the other non-zero helicity component of this correlator is the J plus can be obtained by a simple complex conjugation of this result. Now let's look at 2-point functions in the particular theory of Chern-Simons matter theories. So these are fermionic and bosonic theories coupled to the Chern-Simons gauge field. And the 2-point functions in these theories have been computed in this reference marked in red. And they were reported to be this. Now, if you convert this into spinor helicity variables, it takes the form which is given here. Thus, we see that in spinor helicity variables, the 2-point function in the interacting theory is given by the 2-point function in the free theory, dressed with an appropriate anyonic phase factor. Now, this is for the spin 1 case. It can be seen that this generalizes to our 2-point functions of arbitrary spinless currents. Now that we have discussed 2-point functions, let's come to 3-point functions. Here we need to introduce the idea of homogeneous and non-homogeneous contributions to a 3-point correlator. So in a 3D CFD, we can split a correlator into its homogeneous and non-homogeneous pieces, as shown here. And this comes from the action of the generator of special conformal transformations in spinor helicity variables. So if you take your generator in spinor helicity variables and act on a correlator, it is not zero, but what it gives is terms from the 𝗦𝗲𝗀𝗀𝗪 identity for the correlator. And the homogeneous part is, as the name suggests, is the part that is killed by the generator, and the rest of it, which contributes to the 𝗦𝗲𝗀𝗪 identity, is the non-homogeneous contribution. In the DS4 language, this corresponds to, the homogeneous space corresponds to, say, the Einstein gravity, and the non-homogeneous space corresponds to the W-cube contribution. Now, one can check that a 3-point correlator satisfies the same 𝗦𝗲𝗀𝗪 identity in the free boson and free fermion theories. This implies that their non-homogeneous contributions are the same, since the non-homogeneous contributions are given by the 𝗦𝗲𝗀𝗪 identities. Now, the homogeneous contribution is uniquely determined up to a theory-dependent coefficient for a given correlator. Now, if we combine the above 3 bullet points, we can write the 3-point correlator of the stress tensor in the free boson and free fermion theories as the sum and difference of the same non-homogeneous and homogeneous pieces, as we have shown here. And this has also been checked by an explicit computation of these correlators in the free theory. Now we make use of these expressions for free boson and free fermion in terms of homogeneous and non-homogeneous to write the 3-point correlator in a generic CFD as in the last line. Now what we can do is, as was mentioned, the relation between the parity even and the parity odd parts of a correlator are made manifest in the spinor helicity variables. So you go to spinor helicity variables and express the odd part in terms of the even part, the homogeneous part of the even correlator, and the relation takes this form. This helps us re-express the TTT correlation function as the sum of non-homogeneous piece and the homogeneous piece as a weighted sum of the non-homogeneous and homogeneous piece, and the homogeneous piece gets this phase factor times the gamma t. So we emphasize that the homogeneous and non-homogeneous spaces come from the free theories, and hence effectively we have been able to write this correlator purely in terms of the free theory. Now that we have discussed 3-point functions in a generic CFT, we'll focus on 3-point functions in Chern-Simons theories. So in these theories, once you have given in the known values of NB, NF, and N0 from the literature, the 3-point function TTT in the Chern-Simons theory takes this form. So here I have written it for the fermion coupled to Chern-Simons gauge field, and lambda f is the coupling. So what we see is the homogeneous piece gets the anyonic phase, and this interpolates nicely between the lambda f goes to 0 theory limit and the lambda f goes to 1 theory limit. So as you can see, as I have illustrated in the picture, when you take lambda f goes to 0, the correlator gives you non-homogeneous minus homogeneous, which was how you had originally had your free fermion correlator. And when you turn on lambda f, it gets it comes out of here, and once you take lambda f all the way to 1, you get the correlator to be non-homogeneous plus homogeneous, which is the free boson result that we had started with. Interestingly, it is the same anyonic phase that appears in the all loop 2-to-2 scattering amplitude in Chern-Simons matter theories that appeared in this paper marked in red. Now this analysis that we had for the 3-point function of stress tensor directly extends to the 3-point correlators of any spinning operator, and the result takes the form as shown here. Okay, so to conclude, we made use of Spinner-Helsinki variables which make manifest the relation between parity even and parity odd parts of a CFT correlator. We use the fact that the correlator can be split into homogeneous and non-homogeneous contributions. And these two factors helped us express 3-point correlators in a generic CFT purely in terms of the free boson or the free fermion correlators. And in the context of Chern-Simons matter theories, these took an interesting form where the correlator is given purely by the free boson or the free fermion correlator appropriately multiplied by a phase factor, which nicely interpolates between the free fermion and the free boson limit. It would be interesting to see if the anyonic structure extends to 4-point functions. And another question we can ask is, can we have anyonic currents whose correlation functions we can compute just as in the free theory? Thank you.
Okay, so we have time for a few questions. So I guess Sunil Mukhi has a question.
Yeah, just a very naive question, since I'm not quite, I don't know the results in detail. But it seems like you have a general result that Chern-Simons, is it a result for general Chern-Simons theories that correlators can be expressed in this form in terms of free boson and free fermion correlators?
Yes, it is.
Okay, and does that suggest that they might have a map to some free theory?
Yes, I mean, I don't think it is known yet, but it will be a good thing to have a free field realization of these theories, yes.
Okay. One reason I ask is that, generic Væsumino-Witten models, so for level 1, we know that Væsumino-Witten models on simply laced groups are free theories, and we know the map. But for higher levels, beyond, 1, 2, and 3 or so, it's generally not the case as far as I know. So I wonder whether this tells us something new about Væsumino-Witten models. That would be quite remarkable.
Okay.
Anyway, I'll leave it there. Yeah, thanks.
Okay, so next Shiraz has a question.
Hi. As you know, there are these the spin S currents obey the kind of equation del J is equal to JJ in general.
Yes.
Plus JJJ. So let's forget about the 3J terms. Do the expressions that you have here, do they take into account the JJ part as well, or is it only for those 3-point functions for which the JJs don't contribute?
This is for all. So this, what I know is this applies for all 3-point correlators where the triangle inequality is satisfied, even if the currents are weakly broken.
And are there 3-point functions where the triangle inequality is not satisfied?
Yes, and there are, like, if you write J4, JJ.
Okay, and so your expression does not apply to that case?
No, sorry, it applies, Renjan. It applies, sorry.
So it applies to every case, including the contribution of that JJ.
Yeah, it's just the distinction between non-homogeneous and homogeneous does not exist outside the triangle. Every correlator becomes non-homogeneous outside the triangle. And you can actually write this non-homogeneous, one of the non-homogeneous free boson plus free fermion, and other non-homogeneous has free boson minus free fermion. You can also identify them just from the free bosonic theory. So this relation is generic.
So for all currents.
Yeah, for all currents, yes.
Thank you.
In fact, you can actually derive the non-conservation, what you pointed out, just starting from the free theory 𝗦𝗫𝗀𝗃 identity by doing some transformation.
So does this suggest that if you redo 𝗦𝗲𝗀-𝗪𝗍𝗪 in spinor helicity variables, the analysis would be much simpler?
So 𝗦𝗲𝗪-𝗪𝗍𝗪 analysis just becomes trivial with the identification. So Renjan has not shown a identification in the momentum space between parity even and parity odd. With that, it becomes trivial. The equations directly, 𝗦𝗲𝗪-𝗪𝗍𝗪 equation directly maps to the free theory equation, and that becomes trivial.
Okay, thank you.
Actually, we have been able to actually do it for the 4-point function as well. So the full 4-point function just directly maps to the free theory higher spin equations also.
Thanks, Achal.
Look, we have 1 minute for questions.
Yeah, just a small question, Renjan. Hi. So is there if you look at the full TTT correlator in the Chern-Simons theory, I mean, is there a double copy relation for that? I mean, not in just in the free limit. I mean, can you write it from the square of the current correlator?
Yes, that can be done. Yes, and
for the exact thing, the whole thing, TTT.
Yes, it has been done. Yes.
I see. And what is the I see? So it's the in the same theory, you look at the JJ correlator and you do a double copy and you get this TTT.
Yes. Right. Yeah.
Okay. Thanks.
Yeah.
Great. So if there's no more questions, we can move on to the last speaker, which is Anurag Kaushal from TIFR. And he'll speak about bulk geometry and target space entanglement. And he has 13 minutes.
Can you see my screen?
Yes.
Okay, thank you. So first of all, I would like to thank the organizers for giving me an opportunity to speak at this conference. I will talk about a set of works which I did in collaboration with Sumit, Sinong, Gautam, and Sandeep. This is the outline of my talk. Let's just jump right in. So what I want to ask is, how do you define theory entanglement in a theory of gravity? In particular, how do you define regions? So because at gravity, the space-time is dynamical and the metric fluctuates, so do the regions. But in the limit of semi-classical gravity, when you have a smooth space-time background, you can talk about entanglement of the quantum fields which ride on this background, including that of, including the gravitons. We know a few things about entanglement of quantum fields. In particularly, we know that it diverges, and the leading divergence is an area term. However, in a theory of gravity, one expects that the entropy is finite because the Bekenstein-Hawking entropy is finite, and many people have suggested that the role of this cutoff should be played by the Newton's constant, in particular by Susskind and Nagelum, which argue that what the divergence does is it renormalizes the Newton's constant such that area upon G Newton remains finite. Okay, so within that limit, we ask the reverse question, which is that what is the boundary quantity that gives you the same answer? Okay, with that, let me switch to a completely different topic. Let me talk about entanglement in quantum mechanics. So first of all, in quantum mechanics, there is no space. At a given time size, you have a dot, but you can still talk about entanglement in the target space. So for example, if you have a single particle moving in 1 dimensions, and let's say your region of interest is A, which is x greater than 0, where and you're only allowed to make measurements in that region, then the first thing you note is that the Hilbert space decomposes into a direct sum, unlike a product which you're familiar with in field theory. So the Hilbert space decomposes into wave functions which have support in your region of interest and wave functions that have support outside in the complement region. Moreover, the reduced density matrix takes the following form. It separates into 2 blocks and or 2 sectors, and roughly these sectors correspond to the fact that the particle, if it's in your region of interest, the density matrix behaves as so. If you started with the pure state, let's say, and it behaves trivially, like trivially when the particle is not in your region of interest, and you have to keep track of these factors because the whole density matrix is to be normalized to 1. Given this density matrix, you can define entanglement by the usual von Neumann formula, and in this particular case, it boils down to this. Okay, so but target space entanglement is more general. You can consider it even in field theories by demanding a restriction in the target space where the fields take values instead of where they live. What remains true, just as in the example we saw earlier, is the Hilbert space fails to tensor factorize. However, it does decompose into direct direct sum over tensor factors, like so. So each term in the sum correspond to a different sector. For example, if you have n identical particles instead of 1, these sectors would be labeled by how many particles are in your region of interest. But within each sector, you have a tensor product structure. And and that allows you to define a reduced density matrix sector by sector. So the full reduced density matrix in your region for your region of interest reduces into this block diagonal form. And then again, you can define entanglement entropy in the usual way because you can define sector by sector and then you sum over all the sectors. My main object of interest is quantum mechanics of D0 branes, where instead of particles, you have matrices. These X's are n cross n Hermitian matrices. There are 9 of them, and I have ignored the fermionic part. But let's say what I want to do is I want to consider entanglement in this matrix space. So, for example, if you choose one of the matrix, let's say X1, and you ask, can I ask how this, let's say, K cross K block is entangled with the rest of the matrix, right? So immediately you realize that there are gauge transformations which will rotate this red guys with the blue guys. And so what do you do? Well, what you do is you gauge fix. Because you have these gauge transformations, you can always diagonalize one of the matrices. Once you do, there is residual gauge symmetry. There's Weyl symmetry, which is permutation of the eigenvalues. You can also fix that by demanding that the eigenvalues are ordered. Once you do that, let's say you order lambda1 greater than lambda2 and so on. Now, after you have completely gauged fit, it makes sense to talk about entanglement of these set with the rest. I should say that there is a more gauge invariant definition of target space entanglement, which we talk about in our second paper. But I don't have time to talk about it. But it's much it's a more abstract and better way in some sense. Okay, so now let's look at the dual geometry. So if you have n coincident D0 branes, it leads to the following background if n is very large. It's symmetric. Now, what I want to ask is the question is which I asked in the first slide, is that let's say I choose a region in this background, and I ask what is the entanglement and what is the quantum the boundary quantity, which gives me the same answer as this. Specifically sticking to this particular example. And what we proposed in our papers was that if that the bulk entanglement that you do, that you want is nothing but the target space entanglement in the D0 brane quantum mechanics theory. And the way it works is that once you choose a subregion, let's say A, which is given by f of xi greater than 0, it's some constraint where xi the coordinates of your geometry, in your geometry, it imposes the same constraint, f here is the same as this f, in the matrix theory. X here are now, this capital X are now in percent matrices. To see this, one can look at the low energy picture. So if you remember, the potential term in the quantum mechanics had this commutator square. If you have low energies, you fix that potential to be equal to 0. And what that leads to is that all the matrices are diagonalized simultaneously, and the eigenvalues are nothing but the locations of these ND0 branes, the coordinates of the D0 brane particles. If you have the potential slightly turned on, there will be off diagonal values, and they correspond to the open strings connecting these different D0 brane particles. So, for example, if these are the D0 particles in your region of interest, you look at, they correspond to the diagonal entries here. These open strings, the red open string correspond to off diagonal elements here. These blue ones correspond to diagonal entries here, and so on. So this is a proposal that, given a region in the bulk, that leads to a constraint in the target space, and that leads to an operator algebra, and therefore target space entanglement, which can be computed. And in particular, if you know the initial state, you can find these reduced density matrices explicitly and find the entanglement. Okay, so till now what I said sounds a bit unbelievable at first, but let me give you an example where what I said is exactly true. And it's the example of C equal to 1 matrix model dual to 2D non-critical string theory, which was shown by Sumit in the mid-90s. So the C equal to 1 matrix model has a single matrix, which you can always diagonalize. So either you can work in the matrix space, or you can second quantize it and get a field theory description, and you can calculate the entanglement. It has this familiar log behavior. And you can also calculate it directly using various methods, as was revisited by Hartnell and Nizing. You get the same answer, but the most interesting part is that the cutoff is replaced by the coupling, position-dependent coupling of the theory. So, and if you properly account for factors of in this game, then you would identify this with the Newton's constant. So this is a theory where what we proposed is exactly true. The emergent space is the same as the target space. One more reason we expect that target space entanglement to really be a definition of entanglement in the theory of gravity, in the dual theory, is because while the dual geometry, the smooth geometry exists only at the large coupling and large n, strong coupling and large n, the definition of target space entanglement, it makes sense at arbitrary coupling and finite n. So in principle, it can continue to provide a boundary definition of bulk entanglement. So I'll quickly compare what we have with the standard 𝗦𝗲𝗀𝗃 formula. So the 𝗦𝗲𝗃𝗃 formula is the holographic dual of regions in the base space of your boundary CFTs. For example, if you have a 2D CFT, you have an interval, and the RT surface corresponds to gives the entanglement of that interval. But in the theory that we consider, which is the D0 brane quantum mechanics, you don't have space to begin with. So you don't have RT surfaces, and more generally, you can think of a more general notion of entanglement where you impose restriction in both the base space as well as target space. If you have, and that general notion will interpolate between what the standard entanglement and the target space entanglement. So I would like to conclude by saying that we have a proposal for bulk entanglement in terms of the target space of the boundary theory for DP brane holography where p is less than 2. I only talked about p equal to 0, but we believe our proposal is true for p less than equal to 2. I have ignored the fermions, fermionic part of the action totally, but it would be nice to keep track of them. And as I said, we'd like to have a more general notion of entanglement, which sort of interpolates between the RT formula and what we have. And maybe that can tell us about something about bulk reconstruction in quantum bidirectional. Most importantly, we would like to have a direct test of our proposal because it's analytically, it's very hard to find wave functions in the matrix model. Most likely that test will be numerical. Okay, I'll stop here. Thank you.
Thanks for the talk. So we have a question from ICTS.
Hello.
Hi.
Hi, Anurag. So I had a question. This particular entanglement that you're proposing, is there like a replica trick way of computing it? Should I put a replica in the target space? How should I think about it?
In principle, yes. But that, in fact, that is something that we have been thinking. Is like a sort of a 𝗬𝗫𝗪 type of way of calculating it directly in the target space. But in principle, yes. But I don't have a understanding of it. But yes, that is what we expect. But we haven't been able to do anything or show anything.
Okay, thank you.
Okay, so if there are no more questions, then we can conclude this session and thank speakers for their excellent talks. And I guess Alok can tell us what time the next session.
Yes, again, I'm kind of pushing my luck, but can we please begin at 2:15, 2:15, despite being a half hour, at least a half hour behind schedule? Can we still have a start at 2:15? Will that be okay? Especially Jyotirmay, are you?
Yeah, I'm okay at starting at 2:15, right?
Yeah, 2:15. Savato,
yeah,
2:15.
It's all right for me.
Okay, so all right, and just for our information, a reminder that the post-lunch session is going to be on a different Zoom link and similarly on a different YouTube live link. So the information about the same is on the website. It, I believe, has also been emailed to everybody, and so please use the website to join in with the post-lunch Zoom link today at 2:15. All right, so this is, so thank you. So see you soon in about 45 minutes minus a couple. All right, thanks. Thank you. Thank you so much. Bye. So I think with your permission, I'm going to end the meeting, this meeting, and we will join in with a different link in about 45 minutes. Thank you. So team, we are, I can end the session, right, with your permission, especially.